And so it's really
Yeah, I can't see my screen on there. Can you guys see? Does it look like it's full screen?
It's shared right now, and we can see it like it's the PowerPoint view, like it's not in presentation view or anything. We can see the slides though.
Uh, like, okay.
Your mouse is over between the T and the
Yeah,
O. Yeah.
yeah. It's because it's doing that on another one of my screens. So let me, uh, I don't really know how to get back to where I can see the Zoom options. Hold on.
You might have to like unshare and
Ah,
then
there we
share
go.
again.
Yeah, let's try that.
Great
Oops.
background, by the way.
Well, thank you. Um, where is Zoom? How about now?
That looks good.
Great. Okay, I will begin. Um, okay, so this is my final project, um, cornerstone, whatever you call it. Um, it was a attempt to do topic modeling on annual company reports for the Securities and Exchange Commission for Intrinsica AI, which is a company that does financial NLP and provides a SaaS for finance professionals who are looking to do analysis. Um, so I used the 10K forms. They're a lot like annual reports you might have seen from companies in the past. These are just required by the SEC, and they contain a few different sections, and they have management um, notes. The important part is that they're written by lawyers for the most part, so the language is more what you call legalese than just normal English. So everything is kind of run-on sentences and verbose, and a lot of things that are written to make sure they don't get sued rather than um, to kind of provide information. Um, in this case, section 1A, the second section of the report, is on the risks that the companies face. And these have gotten a lot larger of late because the companies are afraid of getting shareholders suing them for not um, putting out every possible risk they could ever face. So I mean, it's a very rich text to mine, but one of the problems is they just tend to mention risks or not mention them. They don't talk about the severity of them. And the job here was to try to look at um, what risks are discussed in the entire corpus of all these 10K reports, as well as how severe they were or some sort of quantification of them. And that can be difficult when there's no kind of adjectives of severity. Uh, these are the different types of, just an example of the different types of risks that you might run into in 10K reports. So, a lot of them talk about health crises like COVID, um, you know, uh, something like a war, uh, yeah, things kind of as macro as an aging population, that sort of thing. Uh, Obviously, interest rates, financial stuff. Um, so there's been a lot of prior work on this. Obviously, it's a very um, it's a big area with a lot of money involved, and so most of the scholarly work on this in the past has used algorithms. I'll explain in more detail later, but mostly what we'd consider kind of dumber machine learning algorithms that try to cluster together words or meaning. A lot of them are sector focused because topics are different from between like banking or energy companies or oil companies or something like that. They don't have the same topics. There are also businesses that provide this sort of analysis that use AI, but you know how it is. They say AI a million times and don't actually explain what they do. Um, and don't give access. So some companies seem to do a decent job, but I'm not going to pay the subscription fees to figure out if they're right or not. Um, So there was a couple of kind of basic variables to consider when doing this or kind of any topic modeling task. Um, the idea of a taxonomy to start with. So, what risks are there out there? Do I want to build that myself, get it, not have one at all, let the model do it. And then, I needed some sort of code to identify risks, some sort of model to identify risks, and some sort of model to quantify the risks. And there's different ways to go about this. One is kind of a bottom up approach, which is what I would call the less sophisticated models, where you just take the entire corpus and try to essentially cluster it into discrete topics that you see repeated. And the other one is kind of top down, where you start with a taxonomy and you try to match that to different parts of the text. And that's a lot more of an LLM strategy, or the more sophisticated algorithms. So LDA, latent, I don't know how to pronounce that word properly. I've heard it a few different ways. Dirichlet allocation. So we'll just call it LDA. It's a pretty simple idea. It basically clusters together groups of words, but the groups of words have to coexist in a document. They don't necessarily have to be close to each other or otherwise related, and these are very large documents. So you can see on the right side here a few examples of, after going through all the hyperparameter tuning and trying to make the model as good as possible, you get a lot of what I see as basically nonsense topics, things that may have some relevance together. So, sorry, in LDA or in BERT, what we're going to talk about, BERT topic next, you get back a list of words and their probabilities of occurring in a document that is about a particular topic. So I left out the probability. It's not really important for this sort of presentation, but these list of words comprise a topic, according to the algorithm. And as you can see, there's not any really clear topic here. And one of the issues is that LDA tries to look at, it basically assumes that there's one topic per document. And when you have a document, this particular section in the 10K report that is going over many different risks, you have many topics, and that doesn't tend to work out so well. There's other reasons. This model just uses words. It doesn't have any kind of semantic intelligence. It doesn't understand the meaning of words at all. So it just tries to cluster together the same words that it finds, and that limits its ability to just limits its intelligence. So it's an example of what happened when I just did the whole documents with LDA. There was about, I think, 400 or so in my corpus, millions of words of text. But one way to improve on this is to just chunk the documents into smaller documents. And I tried various pretty small chunks of 50, 100, or 200 words. 100 words came out to be the best. It was basically the size of a paragraph. And, as you might think, usually one risk kind of theme is discussed per paragraph. And so it's a lot easier if you look at things in 100-word chunks and are using a model looking for, one risk per chunk. And this came out with much more coherent risks. As you can see, I put two examples in there. For LDA, you have to input how many topics you want to pull out. And my models were always having the best metric scores, like the best kind of accuracy scores with a low number of topics. I think in this case, it was 20. It's a little bit weird. I knew there were many more risk types in there, but the way the models work, it pulled out 20. And so they were pretty general. As you can see, the first one kind of has to do with like property and real estate, perhaps insurance related to property and real estate. Not exactly clear. The second one is pretty clearly about shareholder risks. So, does the board screw something up? Does a director or stockholders decide they did something wrong, sue them? Does the share price go down? That sort of thing. And kind of share price risk is a very large general idea of, well, it's more of a consequence of the risk, but I think you know what I mean. So this did a much better job, but if you're trying to go through and quantify these things and identify discrete risks, and you're getting very general lists of words, it's basically not enough to do a good job, a kind of job that investment analysts would be happy with. You could go through and say, okay, these 100-word chunks represent this topic, and you would get a very broad, kind of not useful group of chunks. And you could say, okay, then in this document, this full one text, this full 10K report, they mentioned this risk this many times, but you'd end up with just a pretty low quality version of what we were going for. So this has been done a lot with corpuses of text. Most of the time, what happens is people will go through and name these risks after they look through the words manually. And, there can be any number of words that, have a certain likelihood to be in a topic. And so it's kind of an art rather than a science to say what these represent, what actual topic these word clouds represent. So I wasn't very impressed with this particular method and moved on to try some other things. So BERT is a transformer model. It takes words and, well, text, and does what's called embeddings, which it turns the text into vectors of numbers. And it does this based on, it's trained on predicting hidden words. And so it has a bit better understanding of context. It has a semantic understanding of, it can vary how much text is included in one vector, but it will basically understand units of meaning and group those together, cluster together different meanings. And so you can see it came out with some lists. Some include bigrams, you can see with the underscore, which is always a good thing to do in NLP, is to put together common groups of words, bigrams, trigrams, etc. You can see the forward-looking statements thing. But the problem with BERT, or one of the problems with BERT, is that it's unable to really understand the difference between what text that discuss a risk and text that discusses consequences of a risk, or kind of just boilerplate legalese around a risk. It's not really able to understand what any of this means. So it has a limited contextual understanding, and it basically just clusters together things that commonly go together. And that could be, something like Northwest Florida that has nothing to do with anything for us, and really has no relevance for risks, as far as I understand. And so this didn't work super well either. So I moved on to using LLMs. This was a lot more interesting. Here's the basic idea is pretty obvious, right? You cut the corpus into chunks, you feed the chunks to the LLMs, and you say, hey, what are these about? What risks are in here? And if only it were that easy. So there are lots of issues with models, as we all know, working on them. One of the major issues with LLMs is that it's very hard to get them to respond in a standardized format. And if you're trying to programmatically put something together where you can spit things back to the LLM and quantify things, a lot of times you run into formatting problems where the LLM will answer something in a way that's difficult to parse. I don't know if anyone's worked with LLMs, but this happens all the time in my experience. Even if you say, hey, give me back the risk just in 2 words, with a comma, it will give you back whatever it wants, even if you change the hyperparameters to ask it to be at least creative and least random. Another problem you run into is token and attention limits. So if you're using GPT-4, there's a pretty tight, in my opinion, token limitation that you can just go over. So if you give it too much in the prompt, it doesn't work. And then for other models, GPT 3.5 or whatever, it just won't do as good a job when the prompts get too big. It just can't pay attention that well. Even GPT-4 has problems with that. And then just accuracy in general. These are not perfect or even close at understanding nuanced language, especially because this language is written in legalese, and these models are trained on regular English as well as some legalese, but mostly regular English. So this is kind of the process I tried first. See if I can get a little highlighter pen here. Okay. Yep. So we have two kind of separate processes that are split here. So what I did was create kind of an iterative loop. So I would put in new text chunks from the corpus. So chunks of 100 words. I think this was actually a lot bigger for this particular one. And then I would give the LLM the highest level risks. So very major general risks, like financial risks is one category. I wouldn't go down to sub risks of that because I was just trying to give it a very broad idea to keep things in, and you'll see why in a minute. And then I gave it a starting list of responses for two reasons. One, so it could start to merge things. I wanted the LLM to be as concise as possible, not create many names for the same risk, and also to show it how to format its responses. So I gave it its responses were supposed to be the risks it found in the documents, and I gave it a list of how those were supposed to be formatted. So some examples. And I find that the more kind of examples, you have to be very, very clear in your prompts, and examples helps that. So I would prompt it with these things. So here are the text chunks. Here are the higher level risks you can choose from. And here's a starting list of risks that you can either, and its job was to identify new risks that weren't in the list already. So, you'd query, that's here, goes into the query. Then you'd get a response. That response had to be parsed. So you have to create a function with some regex or whatever to try to pull out the risks in the same format so you could add them to the list. And then you continue to add to your list of risks that the LLM is finding as you give it new text chunks. And so these things are growing, right? The prompt is growing as the LLM finds new risks, and that obviously starts to get towards limitations with either attention or tokens, the amount of text you can give the LLM before it either starts making mistakes or you go over some API limit. So I would build in also a consolidation function. After that went through about 10 times, it got too big. The prompt got too big. And that would take all the list that it had ended up with after 10 iterations of giving it new text each time. And it would have this big list of risks, hopefully formatted in the correct way. But then it would have a function to format them. This was also, I would ask a smarter LLM, usually GPT-4, to format them properly and merge anything that was similar, right? So if they were, you'll see later on, if it was, calling the same risk two different things, like let's say it would say one risk it would call like, I don't know, a corporate governance risk, and then the other one it would call like board member risk or something like that, which tend to be very similar things. Those would need to be consolidated. They would need to be merged. Otherwise, the list would get way too big and we'd have tons of repeats and it wouldn't be useful. So that would all go into this final list, and we continue to go through the corpus. But each final list was separate, right? because these were all one single iteration. So you'd end up with one of these, and they had to be consolidated again to get out with a final list. So a lot of this was just parsing and consolidation and coming up against limits and how much text you could give the model. So I had to come up with a way to create category levels of risk, which is what I meant here when I said I gave it the highest level. So I would ask it to pick one of the highest levels and then make up its own lower level. And I would go through and divide all the risks it gave me. So it would, let's say it gave me 200 different risks. Each one would have a higher level and a lower level and then a description. And since I couldn't feed it that full 100 because that would be too big for the model, I had to divide that up to then consolidate again. I know this is getting very complicated, but doing the best I can here to explain it. And so, for example, I would take only the financial risks from this list and give it to GPT-4 and say consolidate these. And then I would give it only the geopolitical risks and tell it to consolidate those and so on. And, you know, the idea was to come out with a final list of discrete risks that didn't overlap. This did not work all that well for a number of reasons. One was just general accuracy. The models over many iterations would miss things, especially when they only had a very high level risk taxonomy to start with. There are obviously prompt limitations that I talked a lot about already, and then consolidation accuracy. So it's actually very hard for these models to do a good job saying these two things are in the same category, especially when the categories get fairly specific. I don't know if it's an attention problem or just an intelligence problem, but I'll give some examples of those in a bit later. I think slide after this one. So these were some of the issues that I found that LLMs would run into. So if you had a list of many risks, so a lot of times at the beginning of the 10Ks, there would just be kind of the company faced the following risks, like in the financial sector, and it would be like credit and interest rates and, you know, shareholder opinions and blah, blah, blah. And it would just be a really long list of different risks. And maybe because there were so many different topics in a small space, the LLMs had difficulty understanding them all or picking them all out. I don't understand precisely why this was a problem, but it was very clear that it was something they didn't deal well with. They had also had problems where a lot of the text would say, okay, the company faces a risk of, you know, loss of shareholder confidence, and then the results of this risk will be all these financial outcomes, right? We'll lose money, our stock price will go down, they'll fire our board, blah, blah, blah. And a lot of times these consequences and which were more of the object, and the risk, which was more of the subject, were confused. And, you know, that makes sense. A lot of the verbiage was dedicated to the actual consequences, and we weren't really looking at that. And so, and then there'd just be, like I discussed before, a lot of randomness and hallucination where they'd either give me a response that was too different from what I asked for to parse in terms of formatting, or they would just hallucinate things that weren't there. And so here's a few examples of where they matched, where they failed at kind of consolidating in the endpoint. So let me just jump back here and show you where that would be. So that would be when I'm giving it these final lists here of things to consolidate, and they're trying to look at what risks should go together. So they would call something ownership structure risk, which, you know, shareholder influence, and then governance risk, which I was talking about, which says ownership structure in it, right? And these should somehow be consolidated, but the models left them separate. And this was even GPT-4 would do this. I think actually these are examples from GPT-4 consolidating. And so, you know, this process just didn't work as I'd hoped. So the next thing I tried was to give a full taxonomy to the models. So basically, they would do a better job categorizing in the first place and not have to do as much consolidation later. And there's not a lot of company risk taxonomies out there. In fact, there's only really one I could find that made that pertain to many different sectors of companies. That was the Cambridge Business School. And so the risk would be divided into different levels. So a class like corporate governance, and then a lower level family, which could be something like how the management performs or non-compliance, and then a type. So specifically, they don't comply with emerging regulation or there's negligence. Basically, they don't follow some compliance rules. Management could be executives make a mistake or the board makes a mistake, right? And these could all be risks that would cause the company's problems. So I had to find a way to feed the LLMs this giant taxonomy. All of these had definitions and details, and there were, I think, something like 200 types when you got down to it. So that was another sort of challenge of coming up against how much text you could give the models in prompts. I notice I'm going way too slow here, so I'm going to speed up. Sorry. Um, in short, I gave them one level at a time, and they had to first look at text and identify the highest level categories. Then they would look at the same text and look at the lower level categories. That way I could take the lower levels under the specific higher levels it had already identified and spit it back that way. So it would basically limit the amount of text I had to give it by going one piece at a time. And this actually worked decently. Here's an example kind of response from a chunk of text and the risks. So you can see the colors are the risks that GPT-4 found through this model. So they're fairly accurate. They are, you can see there's still some text in white, and some of that is just either should have been an other category or it just missed. That first thing, like at the top, it could have called that. Well, there's a few it could have chosen, but kind of cybersecurity risk at the top there, it missed, and a few other places. But it generally did a pretty good job. I think a good enough job to create a product out of this. Unfortunately, giving GPT-4 the same giant corpus 3 times over to categorize at lower levels each time was too expensive, and would not work for the company. I think would have ended up being in the range of, I think it was like 4 or 5 grand, US dollars to run through the API just for the subset of the 10K reports that I had. And so it didn't really make sense to move forward there. So I tried to come up with a new methodology that mixed these approaches, so that I could save money but try to maintain the same level of accuracy. And in short, that was basically to come up with lists of keywords for each risk. So I took this Cambridge risk taxonomy of 200 risks or so, and I said, hey, GPT-4, take this particular risk and give me back a list of terms that you think would be used in a 10K in text discussing this risk. So if the risk was, cybersecurity, it would give me words like spyware or malware or security breach or data breach, that sort of thing. And then I would use BERT to embed these terms and go back and try to match the embedded keyword lists to the embedded corpus of text. So everything would be turned into a vector, and you'd use semantic similarity to say, hey, this sentence is probably talking about this particular risk because it's semantically similar to this keyword list. Again, this was actually a lot more complicated than what I just explained, because everything has to be done iteratively and in smaller chunks with these models. So the first thing was what I just explained. GPT-4 would go through and say, hey, here's what I think the keywords would be that would discuss this risk. And then I would turn those into embeddings. So we have the keyword risk lists as embeddings, 200 of those. And then I would go through and embed the entire corpus as well. Each sentence would be, chunk into each sentence, and those would be vectorized as well. And we would match them. And that did okay, not very well. So the second thing I did was go back and try to improve on those. So I would give GPT-4 examples of actual text that did represent a particular risk. So if the risk was cybersecurity, I would say, okay, here are 10 sentences about cybersecurity. And I did that by taking the highest semantic similarity scores. So these things would give me a semantic similarity score from 0 to 1. And you would take the 10 sentences from the entire corpus of 10Ks that did the best there, that had the highest scores, and they were almost always about that specific risk. And so I allowed GPT-4 to use real examples to improve its keyword lists. And I worked with it. I did that via the UI because I had some input and wanted to change things. And then we went back and basically did the process again, where we go and look at how the new keyword lists, the improved keyword lists, match up. And I had to take care in this part of, actually, I'm just going to skip over this because we don't have enough time. This is basically just still some improvements in the model, making sure that the risks that Cambridge gave me were actually risks that were relevant to these 10K reports, because there were too many. So some got merged, and that was partially manual. And so I got to a point where I had an approved set of keyword risk lists, so risks that I wanted to use, and went through again, and that was more like, I think, 100 or so, and redid the process again of embedding everything and checking the semantic similarity, and came out with a data frame of every single risk and how similar that risk was to every single sentence in the corpus. So the problem was trying to understand. So for cybersecurity risk, for example, cybersecurity is going to be very similar. That list of keywords is going to be very similar to sentences about cybersecurity. It's going to be very dissimilar to sentences about, I don't know, shareholder risk, right? But I needed to know programmatically at what point in kind of a falling similarity score as you go across all the sentences, things changed from accurate to inaccurate. So at what point, let's say a 0.9, you knew that it was accurate, the sentence was actually talking about a cybersecurity risk. At what point of semantic similarity score, maybe 0.7, 0.6, whatever, did it change to where you would be sure the sentence wasn't about cybersecurity risks? And this was a very difficult thing to do programmatically. And I did it a few ways. One was if anyone's familiar with like binary search method, basically to summarize, I would give an LLM examples of different levels of semantic similarity scores. So I'd say these 5 sentences come from semantic similarity scores of 0.9, and ask it, hey, do these accurately talk about the risk we're looking at? And if it said yes, then I would go down to, 0.8 or something like that. And I'd try to hone in on, by moving that kind of needle, hone in on the point at which it changed. And that was tough. I did a bunch of different functions to get there and never really got that done properly for a number of reasons, mostly because the semantic similarity wasn't a good guarantee of accuracy. So sometimes it would say, oh, 0.9 is a very good semantic similarity score, but it would actually be a false positive. The sentence wouldn't actually be about cybersecurity, even though it had high semantic similarity. Um, so worked on that. A lot of false positives, like I said. A lot of this was due to the same sort of issues we saw before, which is just the confusion between what was the subject of the sentence and what was the object. And, a BERT model is not going to know that. There was just difficulties with contextual nuances. That's kind of the same thing. So one of the problems was, when you would include some of the common consequences of a risk in the keyword lists, consequences of different risks tend to be the same. So no matter what risk it is, it's going to hurt your share price, or no matter what risk it is, it's going to hurt your profits or something like that. And so that would cause confusion because you'd have a lot of the same text or the same meaning reflecting different risks. I came up with a methodology that I won't go through to count these sentences after the fact, but I really never got to that because none of these methods did a good enough and affordable job. So last thing, there's a lot of future work. I think the process of any kind of difficult NLP or LLM work is to just hone in on like making small improvements to the whole methodology. Each time I built something new, there were better parsing functions to get, better responses, better consolidation functions, like different ways of doing things. There's a million different methods I could try and orders of things with this. It's very creative. I enjoyed it, but just kind of infinite work in the future. So I would have, if I had more time, I would have tried, and more money, I would have tried other LLMs. There are many. Some allow a lot more text in prompts. I'm kind of skeptical that they would be able to parse all that text, but Gemini allows something like 1 million tokens or something crazy like that, and I didn't get to testing those out. I mostly used OpenAI and some local models like Mistral. I wanted to look at using grammar models. There are models that can kind of separate the subject of a sentence from the object of a sentence, or the subject of a paragraph from the object of a paragraph, and that would be very helpful. There's also kind of BERT related models that will paraphrase things, and that might have helped kind of just lowering the total amount of text would have solved a lot of problems by summarizing it. There's definitely a lot of human work that could have been involved. Mostly around creating a better set of categories that risks can fall into. And then, also working on those keyword lists. One of the big problems that I found was that the text, most NLP text is totally unformatted. And that was the text I got for this project. But actually, in this case, kind of units of meaning are reflected in paragraphs and headers. So it would have been really useful actually to have those headers set out in a way where, an LLM could know that those were the headings. And for me to be able to chunk the text into distinct paragraphs. So if I could, instead of just picking 100 words, I could say, no, paragraph by paragraph is how I want to chunk it. Those paragraphs would tend to talk about one risk, and that would have been very useful. Unfortunately, re-extracting the entire thing was actually somebody else's cornerstone project in the first place to just extract this stuff. And then there's all kinds of other methodologies out there. It's not exactly straightforward to do this, but when you're using embeddings, there are ways to overweight certain things. So if you think of a keyword list where you're including the risk and the risk's consequences, you would want to have more weight on the actual risk, right? Because that's more important. And there are ways to do that. And there's a million other methods that could be used here. I think the moral of the story here is that, this was possible to do and will be possible to do, especially as, GPT-5 comes out and the prices go down for more advanced LLM models. And the LLMs are just so much better at understanding language and context um, than any other kind of topic modeling, clustering, even somewhat semantically intelligent models like BERT. That it probably makes most sense financially to just wait till the next two or three iterations of LLMs come out and use them, and just give them the entire corpus in the way I did with, in an iterative, repetitive sort of way, and let them do their thing, um, and kind of, improve things around the edges, than to try to find some lower cost method where you mix the smartest algorithms with the less intelligent algorithms to try to save some money, which is what I had done with my keyword method. Overall, it was a super interesting project. The first time I've done real NLP work. Got a chance to work with all the APIs for OpenAI, and yeah, I'll take questions.
Awesome. Great job and congratulations.
Thank you, Cole. That was all
Question?
repeat for you.
Yeah. That's why I'm here. Questions from the floor.
Will, I had a question. It seems like, I mean, throughout this, you're interacting with all of these models and machines and these artificial intelligences, but the other intelligence that's in the picture is your own, and relying on your own sort of reading comprehension and your ability to sort of work through these texts and distill the main points from these paragraphs. I mean, what did you, I'm curious, like where you saw your own intelligence, your own reading comprehension sort of factoring in where were the critical points where you felt like that intelligence, your own, was really playing a big part in this?
Honestly, I don't think my intelligence was used in that way because it's just too much for me to read. I think my intelligence was used in the methodologies, in coming up
Mhm.
with the right ways to present this stuff and prompt, and create kind of these iterative processes where I could give the models enough for them to do a good job with, but not too much, and get
Mhm.
back something kind of intelligent. So it was basically like algorithm building. That was my job, and prompt engineering, and parsing answers and stuff like that. As far as understanding the text, I mean, there were definitely, this is not easy text to understand. I have a background in finance, and so I mean, I don't, honestly, I don't think anyone with any background could probably understand this stuff. It would take a little more study maybe, but it's not, it's not like biotech or something like that, where most of the vocabulary is, the jargon is stuff we're used to. So yeah, I mean, domain knowledge definitely is important, but not vital in this sense. I think that the intelligence, and I think this is often the case for work with, large language models and going through big corpuses, is how you're developing algorithms to efficiently attack this without overwhelming the model, or getting false positives, or and then breaking things. The things I spent the most time on were these kind of, processes that I showed earlier, of, yeah, something like this, or these flow charts of how I'm breaking up the process of saying, hey model, read this and give me back the risks. It's not at the point yet, and it very well may be soon, where we can just do that and say, hey model, here's a 10K, like give me back all the risks in this, uh, that you think apply to other models. But right now, that's not possible. You can only give it a limited amount of text. You can only expect it to understand a limited amount of things. It needs to consolidate its own answers, that sort of thing. And so that was kind of most of my brain power was spent working on that.
Cool. Thank you.
Sure.
Well, how long did it take you for this project? I was just curious.
I don't know, cool. Maybe 2 months I worked on this. Um,
Okay.
yeah, I've gone pretty slow in the boot camp. I've done a lot of I've definitely taken a lot of time on these things. I think the original test was just to do the LDA. So like the first thing I did, that was
Hmm.
what they wanted me to do, and I just was not very happy with that. So I continued on trying to do something that would actually be a product that I could, create, which kind of was not required. But yeah, I think this is like each one of these model and methodologies could have been a kind of project in itself. Maybe I'm just trying too hard, and yeah, doesn't don't need to spend this much time on it. Um,
I'm sure you definitely learned a ton throughout this whole process. Like,
I learned, yeah,
yeah, do you like, for example, since you didn't stop at the beginning, so do you have to keep like going out to like kind of learn different materials all over the places, or how do you kind of learn those
yeah, it's a great
materials?
question.
That's
Yeah,
yeah.
I mean, I'd say 90% of the learning that I've done in the boot camp in general has been via GPT-4 or Claude. I just ask questions, and then if there's things that I can't quite get to, then I'll go look at other projects. I've read papers. I was given some papers, but yeah, I mean, I just say, hey, like honestly, I just say GPT-4, what are the options? Like, what kind of algorithms can I use to attack this? And then I go read into those and kind of look further. I was given a paper that had done this with LDA. It hadn't done a great job. So it had basically come out with these original lists of words that comprise topics, and
Mhm.
they weren't very useful. I worked in finance. I know nobody would actually use that. That they weren't accurate or specific enough, and they weren't quantified. So I just asked questions. I think if I had taken this boot camp 2 years ago, I would have done maybe the LDA and the BERT topic part and been, spent 2 months on that easily, just figuring out how to fix all the errors that code makes and like conceptually understand what these models do.
Mhm.
It's just so much easier to have the LLMs explain things and be able to ask them questions about how exactly does this part work? Please don't speak to me in jargon kind of questions. And that was really what allowed me to get through a lot. As far as like the algorithm aspect of how I would build it, I, I mean, I definitely relied on the LLMs too to kind of ask, hey, would this work? Like, what if I did this? And I have thousands of words of chats trying to go through. Okay, I tried this and it like this happened. So I mean, I this that you're seeing here represents kind of a working full methodology, and I'd say I broke this like many times. In each phase was a different cell of code that didn't work a number of times, as you do in kind of coding projects, and I had to figure out how to make it work a little bit better. Yeah.
Good job. It sounds complicated.
It was, but it was really
Yeah.
fun. I would not recommend,
Yeah.
like, NLP is really frustrating. Words and computers, I don't know, man. They're
Yeah.
they're not they're not necessarily a good fit. Like, I know that's kind of the big thing, and I really enjoyed it because it's not like a regression problem is very math. It's just math. This is so much about how you approach it versus like the technology you use. And I like that. I think that makes a lot of like room for creativity and human
Yep.
creativity. But I wouldn't, yeah, I think in the end, I was just like, let's just wait for the models to get a little bit better, and it'll be a slam dunk.
Makes sense. Thank you.
Sure. Thanks for the question.
Yeah, we're kind of back to the 80s and 90s mentality of just like in 2 years it'll all be fine.
But I think it's actually true this time. Like, because I did get it to work with the expensive model, and uh, they are improving very quickly.
Absolutely. Any last questions?
Okay. Thanks,
All right.
everyone.
Yeah, congratulations, Will. Very good job.
Thank you.
Yeah. All right. I believe so on the schedule, our next presentation is at 4:30. Or was someone planning on going before that?
I was actually planning on going before Will, and I totally missed it because I'm not good at time change.
No worries. I mean,
My apologies.
Yeah.
But if there's time, I'm happy to go now. I can kind of, mine may not be as complex. It's just a Python project, but
Not a
yeah,
competition.
I'm happy to share. And okay, great. Well,
Yeah,
hello
go ahead.
everyone. I'm Katie. I'm not sure if I've met all of you. I'm not sure if I've been on too many of these presentations, so I'm super excited. I'm going to present my Python data analytics project. So I will share my screen in 1 second as I find it. All righty. Okay, present. Ooh, present full screen. Present. Okay, there we go. Let's get on to the beginning of my, all right. Sharing my screen. All right. Okay. Can everyone see my screen? Yeah, okay, cool. All right, so this is my Bay Area rapid train. Oh, you know what? I'm gonna close this door real quick. All right, so I am going to talk about the Bay Area rapid transit system. So let's go ahead and get started. Well, first I kind of want to talk about why I'm interested in the Bay Area rapid transit system. That's kind of like our metro system here in San Francisco. I'm really into transportation. I really like the idea of understanding where people are going, where they're coming from. I like being a little nosy. I think that it helps tell a story about our society, where we've been, where we're going to, and kind of a snapshot of where we are today. And I think that through the metro system, we can really track pretty accurately how people are moving about the city. So this presentation is about how people are moving around San Francisco. Okay, so what is BART? The BART is our Bay Area rapid transit system. It connects San Francisco to 5 different counties. So I put a little map. Oh, I lost my pointer. Oh, I put a little map here on the right-hand side. And you can see that it connects 5 counties with San Francisco, as well as 50 stations, 2 different airports, and all using 5 lines and 130 miles of track. BART is funded by state and regional funds, but it is using $1.6 billion emergency fund coming out of COVID. So that runs out in 2025. The expectation is obviously that its funding is going to come from the states and the regions and replenish that amount. I also think it's really interesting to talk about who is riding the BART. So from a poll, 67% of our riders are non-white, 44% of them do not own a vehicle, and 31% of them have a household annual income about under $50,000. And this information is procured from the BART website. I think that's super important because a lot of people rely on BART, especially those who don't have a car, especially those who are coming from terminal stations and coming in and out of the city. So I myself rode BART to work. I live on one of the BART lines. I see people in the morning going to work, and I'm just curious where everyone else is going. I have some other questions about BART, such as why aren't there any kids on BART? Why aren't there any seatbelts on BART? But we'll get to that later. All right, so I just want to talk quickly about the data that I used. So I procured the data from Kaggle, but it is from BART.gov, and it's very simple in its essence. It kind of tracks origin and destination stations, so kind of a unique trip by hour and by date, alongside a trip count. So this information is available in 12 different files from 2011 to 2023. And then from 2023 to 24, they kind of changed the way that they roll up their data. So instead of getting a daily view, I actually only have monthly information, again, with the origin and destination stations and the trip counts, but I don't have that date or hourly cut, which you'll see in the information or the data that we go through. Most of the time, I could use that 2011 to 2023 data to kind of do analyses on a level that's more granular than the month, but I did incorporate 2023 to 2024 on the month level for some of my visuals as well. All right, so let's talk about the goals of this presentation. So I wanted to kind of understand a couple of things. One, which is, what is our historical ridership? What does it look like? How has it changed in the past 13 years, especially with the launch of different various ride shares? Uber in 2010 and Lyft in 2012. I want to understand, what does our historical ridership look like? And then especially, how did it change during COVID and where are we now? I go ahead and examine the stations and examine trips by station and commute type. And I wanted to kind of do a deep dive into San Francisco or San Francisco downtown, because I thought it was the most interesting. The last thing is I wanted to uncover key influencers of ridership volume. What is driving it? What stations are the busiest? What kind of characteristics or what kind of neighborhoods are driving our ridership volume? Okay. So I'm going to dive right in. I wanted to first get a sense of where we are in historical ridership. So this is 2011 to 2024. So I charted our yearly amounts, our yearly trip volume, and then I included month as well, so that we can understand where we are by month and by year. Overall, you can see that our volume is increasing from 2011 up until about 2016 at peaks, and then it comes back down. Now, I thought this was really interesting that BART was continuing to grow between 2011 and 2016. I'm not 100% sure what the drivers of that growth are, but it was interesting to me that, again, Lyft and Uber launched in the early aughts, and I was expecting kind of to see a drop more immediately. We do see a peak at 2016, and it comes slightly down to 2019. So it was a little bit of a surprise to see that we were still growing up until then. I think it takes a little bit more studying to understand what the actual impact of ridership is. That's not really the point of this presentation, but I wanted to bring that in to examine that. And then as we see in 2020, especially in March, you can see just like a steep cutoff on the year, but also by the month. Our shelter in place was March 16th, 2020, and you can actually see that's like exactly half of a month. And so it just comes to a standstill, just screeching halt. So yeah, that's just kind of how we've been overall during these years. Okay, so this is again kind of the same visualization of the data, but by month now. I wanted to show a couple things. One, ridership is a little sinusoidal. It is dependent on the seasons of the months. So you can see that there's peaks kind of at the later part of the year, and then there's valleys. And I think that's consistent with the way that we ride BART. It's most busy in September, most busy when people are going back to school, least busy kind of in the months coming out of the fall into the winter, and then driving up again. I also wanted to point out just how steeply our ridership fell in 2020. So in February 2020, you see that we're at 8.24 million trips per month, and this is a monthly average. And then in March, you see that completely half, and then by April, our ridership is around 624,000 riders. And if you actually total up the rest of this ridership from April to December, that total aggregate of all of those 8 or 9 months is actually just the amount of 1 month in our previous years. So we're just seeing a really steeply drop. And as the years go by, there's a bit of growth. We see kind of some obvious dips. This is where the Delta variant became very prevalent. in the later part of 2021, in the early part of 2022. But you see that we are coming back. I was most surprised by the fact that we are coming back, and we did kind of very quickly that this kind of looks a little linear coming out of it. As we start to look at the past year and a half, that linear behavior kind of starts to shift into something a little bit more, that upward slope starts to kind of plane out a bit, is what I meant to say. So what I'm thinking here is, yes, we've rebounded, but to what extent will we rebound? And when will we actually plateau again? Things have changed since COVID, and I wanted to illustrate that here and kind of give recommendations to our viewers as to what we can do. I want to stop actually and say that aside from you guys, my key audience here would definitely be the BART Board of Directors, so people who are decision makers on BART. Also the City of San Francisco and leadership in San Francisco, as well as anyone who's in the Merchants Association for some of the neighborhoods that I'll be talking about. Okay, so just to view it a different way, I wanted to go ahead and chart the weekly trip count. So here we're in the month. Wanted to kind of look at it by the week and illustrate a couple of things. Again, this growth. So each one of these dots represents a weekly trip count. And so I have 52 of these dots, one for each week of the year. And so in 2011, you can see that they're represented by these yellow dots, and then 2016, they're represented by these dark dots. And what I wanted to illustrate here was just the kind of arc of a ball, really. It kind of rises to 2016 and it drops all the way down. 2020 here was definitely our lowest year, and we just see very, very small ridership as a result. I also wanted to show that on the week, I wanted to show kind of the variance per year, the weekly variance. And I also constructed it here per week. And so this is an attempt to, it's probably overkill for this project, but I decided to perform some t-tests to understand if ridership has changed significantly and in what years. So just before I perform that test, I want to show a variance of all the data points by year. So starting from 2011, we can see that things kind of follow a pretty normal curve. There is a little bit of kind of like a small hump here. There are weeks at the beginning and the end of the year that may not be 7 days long. And so I did see some irregularities there. Interestingly enough, in 2018, the distribution kind of widened, or sorry, not 2013, the distribution widened, and then it kind of narrowed down again. So people are riding pretty consistently, and those who are riding are using it in a very consistent manner. Here in 2020, you can see that's different. You can see that it's kind of all over the place. And that's because we experienced such a drastic traumatic shift in 2020 and building back up to something that looks pretty normal and pre-COVID. So I think for me, my understanding is, 2020 kind of shook it all up, but we're kind of returning to what we were before, or we're returning to the similar behavior. I think the question now is how many people are returning to this type of behavior? I'm going to breeze through this next part, partially because I want to stay on topic, but I did perform a t-test. I evaluated year on 2011 to 2012, whether or not those weekly amounts changed. I performed a F-test as well as a 2-sample t-test. And if you care to see it, this is my results. Sample 1 is 2011, sample 2 is 2012. I do that year over year for all of the subsequent years, and I kind of charted and highlighted the ones that I thought were statistically significant. You can see that actually in 2011 we grew a lot, 2011, 2013. But by 2016, that during our peak, as this graph will show you, we reached our peak, and then we had a sizable decrease in 2017. Also, I will say that in 2020 to 21, it also is a very compelling result to show that we've rebounded, and we've rebounded very significantly. Again, the question is, okay, we see some decline here. We see some growth coming out of it. The expectation that our ridership is going to return to, pre-pandemic times is probably, not likely. And so the question is, where is it going to turn out, and what are the factors? So I wanted to understand our rebound or our growth. And so what I did was I actually divided our pre-pandemic numbers, our post-pandemic numbers with our pre-pandemic numbers to come up with some sort of ratio of rebound. I only did it for a couple months because I wanted to include 2024, and we're not through 2024 yet. So I included data points from January to April because of that sinusoidal behavior. I didn't want to include all data points. And I wanted to see where we were starting from in 2020 and then where we ended up in 2024 in an attempt to just plot a very simple trend line. And if that trend line is correct, we are growing by about 1.2 million monthly riders per year. And that would put us kind of returning to full ridership around 2027. I think that is probably not going to happen because, as we see in our earlier slides, it's kind of this amount is going to plane out. But if we were to plot actual trend line to our January to April numbers, this is where we'd be at. I think the reason why it's so steep is because in 2020 to 2021, there was that great jump. So what are the key factors in growth? And, when will our trip count plateau? That's kind of the questions I want to understand. And also, where are people coming and where are people going to? So the next thing I want to do, hopefully, let's just imagine that there's a map here, because there is. I'm not sure why it's not loading, but I wanted to understand trip volume by station. So remember, in our data, we've got origin station, we've got destination station. So I went ahead and calculated trip volume per station. I'm gonna just pull up this map so that we can see it. So a lot of the graphics or the visualizations will show kind of this shape of this graph. So I want to look at it. We have San Francisco in the middle. These are the 4 downtown stations of San Francisco. And then we've got a little bit of southern San Francisco as well as our airport. And then that crosses the Bay Bridge. And then we have all of the East Bay. We have our terminal stations, Richmond, Antioch, Dublin, and Berryessa. I actually went cherry picking in Antioch a couple weeks ago, and it takes about 1 hour and 20 minutes to drive out there, and it takes about 1 hour and 20 minutes to ride out there. So it is far out, and I think it's very valuable for those who live far away. So again, San Francisco downtown, Oakland downtown is pretty busy. And then these outer areas, especially Dublin and Antioch and Berryessa, think of those as our very outer suburbs. Okay, so just keep that in your mind as we proceed to, again, if there was a map under here, you would see San Francisco, downtown Oakland, and our outer suburbs. And so the idea was to kind of chart population, not population, just station, basically ridership by station, and understand how it's changing in the beginning of the day versus the end of the day. And so on the top here, I've got an evaluation of 2019, and I use 2019 because I think of it as a pre-pandemic value and assessment. We've got a lot of, I charted kind of the longitude and latitude. So this is kind of a map representation. And then the size of the circles here is the volume. So the size of circles are relative to the volume. We see a lot of volume in San Francisco downtown. We see it in Oakland, and then we see some volume in the suburbs. And this is for the morning time. This is for the morning. So what you can see here, I lost my blinker again, is that people are kind of using the BART station equally in the morning time as an origin. In terms of their destinations in the morning, it's mostly consolidated to San Francisco downtown. In fact, you can see just a big, change in size. Everything else is kind of a small dot, and then you see it grow, centering around San Francisco. And then this is kind of that same graph or same visualization, but in the afternoon, in the hours of 12 p.m. to 12 a.m. And what you can see is it's kind of like an inverse. There's really not that big of a change. And I think that that just kind of underscores the fact that people are truly using BART to commute, to go somewhere in the morning and come back from that same station. They're, you know, though they may travel from station to station a bit, I think that the volume at the beginning of the day is basically the inverse of that evening. I wanted to also compare 2019 to 2023. Looking at it, it kind of looks the same. It kind of looks very similar. Granted, these the bubble sizes are actually relative to monthly volume. So remember, 2019 is high volume, about 9.8 million riders per month, whereas in 2023, it's about 3.1 million riders per month. So yes, the total amounts that are very different, but the actual distribution of the riders and the way that it looks on our map is not that different. So again, I think that post-COVID, people are coming back, they're kind of exhibiting similar behavior. I think that this this visualization provides us kind of as like a first, 10,000 foot view of what's going on. But I actually want to understand now in terms of kind of stepping away from station volume, I actually want to understand where people are going. How are they using this BART differently? So I assigned, I was able to assign whether or not they used it within their own city, within San Francisco, within the East Bay, or kind of as a trans-bay mode of transportation. So again, just comparing 2019 to 2023, I look at the number of trips that are within San Francisco or intra San Francisco, the number of trips that are intra East Bay, and those that are trans Bay. These are both on the same scale. I want to give you a kind of a sense of where we're at. Basically, the majority of our riders are using it to cross the Bay Bridge. And just as a note, again, these riders don't have cars, right? 44% of them don't have cars. And also the Bay Bridge is kind of costly. It's like $8. And it adds like about an hour. It takes about an hour to get across the bridge. So a lot of people are depending on this transit system to get across the bridge. And then within those two sides of the bridge, people are using it actively. I think what's interesting is that this is kind of the distribution throughout by weekday, by weekend, by year. It's very consistent. People are depending on this. It's kind of a lifeline. It's part of their daily lives, and it's very important to them. So to get really granular on maybe the distribution of the Trans Bay, East Bay, and intra populations, I went ahead and normalized it. So this is just the same information, but kind of on the same, in terms of percentages. So I want to see like, hey, truly has it all stayed the same? And what I'm seeing here is the top visualization is 2019 and the bottom is 2023. So we can see that Trans Bay activity has actually decreased. In 2019, on weekdays, Trans Bay trips made up 55% of total trips, but now it's down to 52. So it's down by 3 percentage points. As well, on the weekends, we see it decrease as well. People are staying within their areas a little bit more. People are not using it to commute across the bridge as much as they used to. Oops. All right, so where are they going? I wanted to, since I had origin and destination information, I wanted to go ahead and chart a heat map of where they're coming and where they're going. So lots of colors here. On the bottom, we've got origin stations. So these tick marks are actually each and every single station. And then on the y-axis is our destination station. And this is for the AM and this is for the PM. So let's just take a look at AM for a second. We see that most of the riders are kind of following this band right here. So this is downtown San Francisco is kind of shown in this band, these stations in Embarcadero, Montgomery, Powell, and Civic Center. So they're mostly concentrated here. Everyone is not everyone, but a large percentage of people's destination is actually Embarcadero, Montgomery, Powell, and Civic Center. You can see here, this is basically Trans Bay traffic. This is Oakland stations going into San Francisco stations. This is the suburbs, the East Bay suburbs that I talked to going into San Francisco stations. And then this is the intra San Francisco. So this is people in South San Francisco, people like me that live a little bit outside of downtown, coming into downtown to go to work. I also thought that was very interesting. There's kind of like a very dark dot right there, and that's from Dublin, and that's actually a terminal station. So some people are using it to come in from way far out. Actually, a very large population of the people who come downtown are actually from a terminal station coming inwards. So that is the AM kind of rider. And then we can see a slight band here. This slight band is for destination stations listed here, and those are East Bay stations, so East Bay downtown station. So there's a little bit of traffic, but most of it is consolidated in these 4 stations. At nighttime, it's basically the absolute inverse, where the origin stations are again downtown, and then they're just kind of dispersing right back out. Here we can see a bit of Oakland to Oakland activity as well. So kind of just wanted to chart the areas. And if you put them together, if you put them together, this is 2019 and this is 2024, you can see what they look like. So again, we've got some Oakland SF, we got some suburbs SF, we've got some intra SF. And overall, the visualizations look pretty similar. I think that there's a couple things to call out. One is there's a little outlier here that is actually SFO International Airport. So people are still going to the airport. People are still traveling, probably in higher percentages in terms of the ridership than before. And then also, if you kind of like squint your eyes and look back, you can see that there's a little bit less color over here and over here, meaning that there's a little bit less of that Trans-Bay. So this is, Oakland SF, a little bit of that, less of that Trans-Bay commute, as we saw earlier, rolled up in Trans-Bay, East Bay, and intra-East Bay and intra-SF. Okay, and again, these scales are different. We know that 2019 ridership was, 9 point, well, it's about 3 times as much as now. Or 2 times. All right, moving on. Okay, so now we have this great understanding of our stations, but what stations are actually doing really well and which ones are not? So I, again, kind of compared 2024 numbers to 2019 numbers to attach like a bounce back rate. So I define bounce back as the percentage of rides we have in 2024 to 2019. I know there's a typo right here. And by station. So this is again a trend line saying, hey, overall, our 2024 ridership is at 35% of what it used to be in 2019. So that is what this line represents. Anything under that is not performing as well, and anything over that is performing better. What we can see first and foremost is that there's a large clustering down here of just, stations that are on trend, but they're also just smaller stations. They don't have as much ridership as others have. And then we've got our big 4, I'd like to say it. And these are all actually San Francisco downtown stations. We've got Civic Center, Powell, Montgomery, and the Embarcadero. And Civic Center and Embarcadero are pretty much on the same trend line. But Powell and Montgomery kind of sit on to the east and to the west of that. We see Powell as overperforming. That means that their numbers are doing better than the average in terms of bounce back. And then we've got Montgomery, which is not doing as well. Their numbers are less. And although these stations are very close together, they actually serve very different purposes to our populations. And we'll get into that. But just wanted to show that we've got some overachievers and underachievers. And, let's talk about why, especially for these 2 stations here. Just fun fact, after rolling up all this data, it turns out that these 4 stations downtown, again, there's 50 stations. These 4 stations downtown account for 30% of trips, BART trips. So even though we've got 50 stations, these 4 represent 30% of the volume. And I think that in terms of decision-making, in terms of leadership, kind of making decisions about these stations or city planning, what's really important to note is whatever decisions that they make about these stations or the neighboring areas have a large impact on our ridership, have a large impact on the type of, volume that we'll see coming in and out of these stations. Just a little descriptor about these stations. I threw these icons up, maybe you'll remember them, but again, we've got in order from East Bay to San Francisco. We've got the Embarcadero, which serves both mix of waterfront tourism and retail and financial district activity. We've got Google there, we've got big restaurants, we've got the waterfront, we've got big museums. Then we've got Montgomery, which is mostly all corporate offices. That's where I used to work. There's just buildings there. Maybe there's some small lunch places. I'm always looking for a good lunch place there. There's not that many. It's mostly buildings. And then we've got Powell Station, which is the epicenter of our tourism and kind of links to the cable car as well as all of our hotels. We got big malls there, the Westfield Mall, Union Square, Macy's, all the flagship stores. And then finally the Civic Center, which is for our government jobs and a lot of our city services. So the planning department, health department, all that good stuff is centered in the Civic Center. So what's going on? I charted the ridership, or sorry, the station volume by hour, by day for these 4 stations. I wanted to see what they look like when it was busy and when it was not. So the first thing I did was understand that from a weekday, weekend point of view. On the top here, you can see 2019, and then on the bottom, you can see 2023. In the blue, this is the weekday trend by hour. And then the red is the weekend trend by hour. So no surprise here, we've got 2 peaks, one at around 8 a.m. and one around 5 a.m. This is probably the commuters that are going for their 9-to-5 jobs. And so what we can see is Embarcadero and Montgomery are very popular for that type of ridership. And then Powell and Civic Center are a little bit less. Again, Powell is a shopping station and Montgomery is solely corporate. And then in 2023, it looks very similar. But what I wanted to say was that the weekend activity is actually creeping up a bit. It's creeping up past the weekday activity in Powell Station, and in some ways, a little bit of Civic Center Station. So the kind of ratio of riders are leaning more towards the weekends than the weekday. And I wanted to look into that a little bit more. Again, these are all kind of averages of the days, but what happens when we look at the days themselves? So this is the same visualization, but actually just broken down by day. We've got Monday, Tuesday, Wednesday, Thursday, Friday up here represented by the weekdays, and then Saturday and Sunday here on the weekends. Most notably in 2019, people were kind of just using BART Monday through Friday exactly the same as they used to, maybe a little bit less on Friday, but they were using it exactly the same. Moving to 2023, what we can see is those peaks actually kind of spread into 5 lines, as to say that they're actually following the same types of patterns Monday through Friday, but just to a lesser extent day to day. Fridays and Mondays are the least. So Fridays here in blue, and you can see that its peak is actually almost half the size of the peak that it is on Tuesday. So there's half of the people coming in to SF downtown on the weekdays during those hours as there are on Mondays. And this is really representative of this hybrid work from home kind of model that a lot of the offices have taken up, especially in corporate downtown. That has large implications on who's riding the BART. It also has large implications on our budget and our operational budget. And I think what I'm trying to kind of weave together in this whole entire story is the fact that BART is a civic endeavor. It's not necessarily like a for-profit situation. And for that reason, we have to kind of keep them all downtown. Actually, the BART serves in equal amounts all of these stations in terms of where people live. But a lot of the ridership is actually concentrated, or a lot of the origin destinations are concentrated downtown. So really important to note that ridership is slipping. It's varying day by day. This is likely an outcome of work from home. And we are losing a lot of potential income. Again, we're relying on our disaster COVID relief funds to fund us and tide us through. But our operations are just not nearly where they used to be in 2019. Again, want to also illustrate that these weekend lines are kind of almost higher than the weekday lines, especially for Powell Station. I'm almost done, but I wanted to share a couple things. Number one, again, this is kind of station volume, but what's going on in the area around it? How is the neighborhood around these stations receiving people And so this is kind of an illustration of the inbound and outbound. So trips that come inbound on the weekday, you can see obviously there is that peak that we talked about, but actually there's another peak at 5 p.m. So people are coming in at 8, and then there's an extra population that is coming in around 5. And conversely, what we didn't see before is that there's actually a certain amount of people on the weekday that are using it outbound. So there's small populations of people that live around there that use it as their kind of reverse traffic. But also, since this is Pal Station, what we're seeing is that on the weekends, there are kind of two, there's only one hump. So weekday there's 2, on weekend there's truly just one of inbound people. And the station is most busy in receiving the most inbounds at around noon. So again, Pal Station is kind of a unicorn because, not a unicorn, but it's special because it's actually the one that's doing really well. And it's also a really busy station. So why? Well, everything around Pal Station, especially on the weekends, is shopping and retail. People are excited to come back. And to me, that was kind of a glimmer of hope, that people are actually excited to come back, to go shopping, to gather. They may not be excited to go to work every day, or especially since they don't have to travel to work every day, but when they want to, they will ride BART to go and convene, to get together. And I think that this is kind of pointing to just like a kind of the evolution of the way that people are using BART is, hey, before we used to use it primarily for commute, and that still is the case, but we don't have to as much anymore. However, when we want to actually get together, recreation, have fun, we will gladly convene, we will gladly gather. So weekend trip volume is about 50.7% of that in 2019, the weekend trip volume. And I just wanted to remind you that overall bounce back's 35%, but the weekend trip volume is at 50% of pre-pandemic times. We're almost done here, but I wanted to kind of show some cumulative sums of these two inbound and outbound. So if I charted the cumulative sum here, so you actually see if it was kind of a closed loop system, that the peak amount of people in the neighboring areas comes at around 2 p.m. And this is what the weekend looks like, and this is what the weekday look like. As you can see, this is a sharper curve. That means that there's just more, there's fewer people there, but in that peak time, whereas on the weekday, people are really coming in at 9 to 5, and that population kind of stays constant until they leave. I'm going to breeze through this, but this is Montgomery Station. Again, Montgomery is the one that is primarily just for offices. Again, coming in, large population here that's still here, doing their work, and then going home at nighttime. Okay, so what have we learned? I think that first off, overall ridership is about 50% of pre-pandemic times. So we're about 4 years out from the pandemic. We've returned to 50% of it. We are seeing that there are factors in the way that we are rebounding, and we're seeing that the key factors to changes in ridership are, one, the fact that Trans-Bay volume is down. People are less, proportionately, they're less frequently crossing the Bay Bridge on BART. So they're kind of staying in their areas, whether it's in the East Bay or in San Francisco. So Trans-Bay volume is down. Second thing is that remote work has influenced it such that weekday commute is down, especially on Mondays and Fridays. For the 2 busiest stations, Montgomery and Embarcadero, Friday ridership is at half the volume it was on Tuesdays, Wednesdays, and Thursdays. So that's basic. I think that's the #1 driver of decrease in ridership. Number 3, small glimmer of hope, retail and tourism will help drive volume. So people are coming into the city or using BART when they want to, and for those reasons are mostly because of retail and tourism. So what's to come, right? So just a little bit of update on San Francisco. We have a whole bunch of tech offices that continue to offer hybrid remote, but also are just vacating their leases. So we've got Google just announced that they're vacating their lease. It's about 300,000 square feet in downtown. Salesforce, even though they built a tower, have basically vacated their entire lease. They've decreased their downtown footprint by about 45%. And then a whole bunch of tech companies are also downsizing, and they're continuing to embrace this model. Following that are the large retailers that are now vacating their leases. The Westfield Mall that I actually spoke about, they actually defaulted on their loan. So they actually had to sell. So it's going to be rebranded, but people are kind of pulling out of their leases on the retail side as well. Macy's, which has been here since before I was born, just announced that it'll be selling their building, and they're just waiting for a seller. We've got Uniqlo that closed at the beginning of COVID, and also Forever 21. So there's potentially a lot of vacant storefronts, which would negatively impact this retail hub. And if we're saying that the glimmer of hope is that people are actually willing to convene, willing to come in for tourism and retail, the fact that they're closing is kind of ominous. The last thing is that, again, without these anchors, I think that San Francisco will lose a lot of its pull from neighboring neighborhoods. And that, to me, the most concerning thing is that the San Francisco downtown area is at risk of losing its vibrancy as a commercial hub. Okay, so recommendations. Moving back to this kind of bounce back, I think that the way to really get ridership up is to look at the stations that have the most volume and the people that are those that are underperforming. Again, we outline Montgomery Station as those that are underperforming, and so bringing this up to meet the bounce back or even further will be our biggest struggle, especially since corporate offices are closing. 10 years ago, Twitter set up in mid-market area, which is kind of closer to the Civic Center, and as an incentive to kind of set up there, the city offered that they didn't have to pay their payroll taxes, and that's that kind of small last sum on your pay stub. And so there's different initiatives to kind of attract people to downtown. And so if you identify certain neighborhoods as key development areas, you can attract different businesses there by in a varying amount of strategies. So the goal would be to kind of have focus on bringing more offices back downtown. The second recommendation was to increase that Friday. So we want to pull this Friday and pull it all the way up so that it matches still. Obviously, you can't tell a business to have their employees to come in every single day, but there is a way to kind of attract them. So I think that what we're seeing is that downtown is shifting. It's going to be less office-like, even though we will try to, and it will become more of a retail center. And so I guess the idea is, like, how do you revitalize or reposition downtown? Short term, not a lot you can do, but I think you can recommend to neighboring businesses and shops around there that if they wanted to capitalize on having steady Monday through Friday business, and even Saturday, that offering really good happy hours on Friday would help hopefully attract some of those riders to come in to kind of increase this peak so it is similar to those of the weekday. And recommended hours for that would be from 2 p.m. to 6 p.m. on a Friday. That seems early for Fridays, but I think it's fine. And I've definitely seen people come out on a happy hour at 2. And then again, just making San Francisco downtown the epicenter of recreational activity. Right now, we have a lot of parades that go through there, but San Francisco city-sponsored initiatives like summer night markets or pedestrian-only night areas could increase overall foot traffic downtown and provide an experience that is not easily replicable online. And then the last one is just to increase weekend traffic and interest by, again, maintaining those storefronts and growing retail. And I think there are some initiatives in San Francisco like Vagrant to Vibrant, which are programs put on by various nonprofits to kind of help fill empty storefronts. I think the problem with downtown is that these storefronts are really big and they're really expensive. And so there are initiatives to help fill those vacant storefronts with small pop-ups, with short-term leases, to be able to maintain the vibrancy of downtown, maintain ridership, maintain just overall health of a downtown while we find long-term solutions. So again, that would just be to kind of increase this cumulative sum as well as push those hours out. So if there were events, recommendations would be that they would have them from 11 to 3, where you would capture the most amount of riders and then have their peak audience about 1 or 2 p.m. All right, so final reflection and future steps. Well, I really like this project just because I'm interested in San Francisco. I love San Francisco. we've unearthed the indelible changes of the pandemic and how San Francisco and its neighboring counties are choosing to gather. Super important to note that ridership is down. People are staying clustered within their communities. We are at risk of losing our downtown. And I think that I think it's more of a call to action to show that without city planning or without being proactive, that is going to be what happens. In terms of future research, I think next steps are kind of beyond the scope of this project because it's not really a research project then, but I think if there was anything that we wanted to do was to pull bus information and then also Uber and Lyft data to support the claims that we are having kind of, we are experiencing our downtown decline and fail or potentially fail. So I think those are the two things that I would do to make sure that I feel very comfortable about this data. And the next part is to really, inform others. Anyways, that is my presentation. And I hope you guys are still watching.
Awesome. Great job.
Great.
Now, I will also say I'm from Santa Clara and I've spent much time there. And also I did my undergrad out in the Central Valley. So I have taken Dublin into the city before because I didn't feel like driving. Also, parking at the Dublin station is a lot easier than parking in San Francisco.
So you're one of those riders that were on the outlier dot on the heat map.
Yeah, well, Santa Clara, the closest station was Fremont when I was there. So it's like you can't even take BART. That's the whole Caltrain and BART divide, which always sucks.
That mess. Yeah. Anyways, but yeah.
So the work from home bit definitely makes sense, and like I know from other people that I know, they're hearing about the traffic on Tuesday through Thursday. That definitely matches. I'm wondering, did you think at all about the increase in crime, windows breaking in cars and everything like that? And if that has anything to do with this as well?
With the work from home?
No, it's San Francisco, because the fact that people come in Tuesday through Thursday, that makes sense for work from home. But
Yeah.
separately, like the perception that San Francisco is significantly more unsafe now.
Yeah, that's a really good question. I mean, I'm not sure how that, to answer your question, I did not think about that for this analysis. I actually think about that as like researching what comes out of this, which is what starts to go by the wayside once our downtown fails. So, if you have vacant storefronts, to what extent does crime increase? And that is a great future piece of work to kind of support the call to action that people actually need to do this or else we would have detrimental effects.
Maybe they can convert the office to residential building like what New York's been doing. So people it's only like
Yeah.
live in that area, so there's less crime or,
Yeah, for sure. Yeah. I think that's like a really great, I think there has been talk about that. Really reimagining downtown because there are a lot of vacancies there. Obviously it's kind of a long-term change, but I definitely think that's like a very, very, very salient recommendation. And it has been talked about a lot within San Francisco.
I'll also say that I liked your recommendation about like the hours to add like a happy hour or something to encourage people to come in. Now, of course, that basically you'd be enticing anyone maybe from Oakland, Berkeley, around there, because anyone from, say, Dublin or Fremont's not going to come to San Francisco for happy hour.
Yeah, that's true. I think the goal is to kind of also just help those who actually would have commuted downtown to engage with each other and have an excuse to come in another day or to see each other. I mean, obviously, like these are civic projects. I don't necessarily know if the goal of this is to maximize BART ridership. That kind of seems a little circular, like, cool, there's more people. But it is to convert those who are driving to public transportation. And it also to kind of use this as a proxy to show how our city is changing and where it's going.
Absolutely. All right. Any last questions for me?
Okay, thanks, guys.
Great, congratulations. All right, Leland, I know we are farther out than we had planned, but are you ready to go?
Yes, I am. Yeah, that would be great.
Yeah, take it away.
No problem way. All right, 1 second. I will share my screen. Okay, let me know if it's coming through on your end.
It is.
Okay, great. So yeah, so this is my project that was commissioned with Joey Iacopelli, who's got a diligent CFO company that he was starting, and he provided this data set on acquisition due diligence. It's my capstone project. So a little introduction on mergers and acquisitions. Some mergers and acquisitions from 2020 to 2023. There were about 80,000 of them that were closed for a total of $8.8 trillion. This is distinct from successful transactions that were measured in whether or not the two companies that were merged ended up reaching an expected value higher than that of what they would have been expected to reach individually. So only about 10 to 50% of them reached expected value. So it's a large problem in the industry. The problem mainly stems from there being like a lack of dedicated resources towards small and mid-sized company acquisitions. Mostly they dedicate most of the resources to large acquisitions, so there isn't as much on the due diligence side for small and mid-sized. Accounting firms typically would be the ones hired for this task to run some due diligence on the revenue streams of these companies. And the solution here would be to be able to automate the small and mid-sized due diligence process on so that they don't take up as much time as large and overhead as large acquisition targets. Getting into the process that an acquisition would typically undergo is there's a private equity firm whose main goal is to stay informed in whatever decision the target and whatever company target firm they would look like to invest in or acquire. They would hire an accounting firm, like I was mentioning. They would perform the due diligence analysis efficiently, hopefully, and then the target firm would provide the general ledger data and revenue stream and business practices data that they could provide. The private equity firm would look to be able to be advised by the accounting firm in this entire process, but they would be mostly relying on the accounting firm's due diligence analysis on that before they go into final interviews with the target firm if they decide to move forward. The target firm's benefit here would be to increase market share and diversify their services, of course, so they benefit as well, or at least on the face of the transaction. And there were these, like I was mentioning, the accounting firms involved in automating these process and in automating this due diligence analysis are constantly looking for new ways to automate it and make it more streamlined, so that we can get better expected value out of the chosen acquisition targets. For the specific scenario here on the data set that was provided, who we are is I'm an accounting firm consultant that specializes in due diligence on more mid to small size firms, like I was mentioning, that currently incur the same overhead as large firms, but looking to reduce that overhead. The target audience would be a private equity firm. The private equity firm's main concerns are whether or not the company has a volatile revenue stream. Is it like swinging wildly from period to period? Is its revenue stream inconsistent at any point? Is it sporadic? Are there random transactions in it that make up the large bulk of its revenue, or is it something that's seasonally predictable? And then finally, is the target firm experiencing some sort of reliable growth over time? Is it a good long-term investment? So the specific company that was analyzed here was a mid-sized manufacturing company it had much older accounting software practices, nothing like QuickBooks, that needed to be converted to a more standard Excel format. It was a bit complicated on that, but that was done before it was provided to me. They provided both the general ledger data at one stage and also a trial balance summary of their internal accounting department to determine like account performance and stuff. So I got both of those spreadsheets, both of those sets of data. The accounting firm then manually compiled, which is what I'm looking to automate myself. And what was my job here was to compile the due diligence workbook using automated visualizations, automated analysis. The accounting firm also anonymized this data before this analysis to safeguard privacy. I did not sign an NDA, so definitely needed to be anonymized before it was given to me, or to some extent just like safeguarded in some general way. And then I also anonymized it further to be able to make sure that there's just no chance that any proprietary data is like passed along publicly. And so the accounting firm here assumes some partial visibility into the target firm's like procedures and accounting processes and transaction category labels and everything. So getting into some of the raw data that was provided, here's a summary of all the features. There's a transaction ID, organization, account, transaction amount, a typical internal accounting department breakdown of a general ledger. The main interesting thing that we needed to look at was sales accounts. So some data was filtered out. We completely filtered out all non-sales revenue accounts. Like I was mentioning, anonymization was taking place. So I changed all of the descriptions, labels. I changed all of the organization labels, accounts using keys. And then I multiplied all the transaction data by a random scalar that I'm keeping secret as well. So everything is completely anonymized. And then for feature engineering here, that's a couple of different features that were really important are derived from description, particularly the transaction ID. I broke the first unique, as I was doing EDA, I noticed that some of the first part of the description transaction ID was persisted across multiple accounts and had only 355 unique 2-letter combinations. So I used that, I broke that apart from the other part of description to be able to analyze it further, since it persisted across periods. And then I also created a master time frame from period and fiscal year, so that I had a time frame that was relative across all 4 years of the provided data set. So a total of 46 period fiscal years. And those are the 2 features that were really dominant here, and we'll talk about further. The final transform data set, here's a sample of the final anonymized data set, just 5 rows of that data set with description 1, period and period fiscal year, another engineered feature with week and week fiscal year, which come in later, similarly engineered. Most of the transactions in this data set were really, in this general ledger, were really small. Like a lot of them were below $1,250. So 80% of them. So they just had a large volume of transactions for small transactions. The mean transaction amount was $1,688. So highlighting that. A lot of volatility as well. There were like most of the transactions occurred in the fall. So a lot of them occurred in the fall of each year. November had big spikes, almost 2 times the amount in April. Some of that could be pandemic related, but it just depends. For fiscal year 23, we only had visibility into 11 periods out of the 12. But even despite that, we had more transactions occurred, or just about the same amount of transactions occurred in those 11 periods as the 12 full periods of fiscal year 2020. And so from here on out, just for efficiency, since I mostly worked with period F year and week F year instead of period and week, whenever I refer to period or week, it will be referring to period fiscal year and week fiscal year, respectively. This is a sample of a manually generated accounting firm visualization of their due diligence workbook from the general ledger data that I was tasked with automating and recreating, so that any general accounting firm, internal accounting department, general ledger that was provided could spit out this exact graph, this exact visualization. And so you can see that in Appendix B. This particular visualization shows revenue on the bar charts, which you can see is pretty volatile. It goes up and down pretty dramatically. If this were a software services company, this would be like very, very concerning. Thankfully, it's a manufacturing company, so it could be something to do with the internal accounting practices. Maybe they're accounting for things in periods. That was a main concern of the analysis, was whether or not they're accounting for things in periods that they didn't actually receive that transaction, and maybe due to accounts receivable being delayed or something like that. Also, you can see this is highlighted particularly with fiscal year 2022 and 2023, February. So February being here and here, there's just a large dip like routinely in February of each fiscal year. And right now, visually inspecting, there's no significantly visible upward trend, to the meets of the naked eye, but we'll investigate that later. Getting into subplots of all the organizations, there's 4 organizations within it, with Department D being extremely discontinuous and just constant. So not that interesting. Department B was pretty continuous, but it had very low variability. It was just constant over time. So we kind of isolated Department A and C that were really highly variable and continuous across the whole data set. Here's a heat map that displays the account transactions by period, highlighted in the transaction amount highlighted in shaded in blue. There were three different clusters of accounts, I should say. Accounts 15, 17, and 18 were just straight discontinuous, as you can see down here, 15, 17, and 18. Accounts 1, 6, and 10 were pretty continuous, but didn't have high variability, similar to departments like we saw. And so the main ones that we're really interested in are the ones that are constant and highly variable, being accounts number 2, 4, and 5, being these ones where there's a ton of activity. Similarly, for description 1, drilling into the engineered feature that I was discussing earlier from the transaction ID, the first part of the transaction ID that persists across periods, we saw some of them were really sparse. Like this is a very, very sparse data set, so a lot of them were quite sparse. There were some that were really continuous but had very constant transactions, and then there were just meant like AD, and then there are some that are just straight discontinuous and variable as well. So like CI and EM had decent amount of variability and discontinuity, but of those, there were two that really stood out, being CB and BK. CB had possibly the highest variation by like orders of magnitude than any other description 1. So it's definitely something really interesting to get into. And the only thing to note here is that these are the top 15 description 1s out of the 355 that there are that displayed in this heat map that are based on the 95th percentile. Looking into description 1s, drill down to transaction total, the 4 description 1s of interest to CB, EM, CI, and BK. Transaction total being the first column, also looking at their percentage of total of that description 1's percentage, transaction amount percentage of the total transaction amount over time to just get an idea of how much of the overall they're just constituting at each point. CB had really high volatility for its transaction amount, but in terms of a percentage of the total transaction amount of the data set, it actually was pretty constant over time. So it's just consistently taking up somewhere between 40 to 60% of the overall transaction amount, which is pretty significant. The other 3 description 1s kind of exhibited some low variability. They were total and percentage were pretty similar. So there wasn't something as interesting to take away from those. CB is just, again, is like an anomaly. I also drilled down into some large transactions just to see, since most of the data set was small transactions, there were some large transactions that just kept repeating in different places. So it was really interesting to just get an idea of what's going on there. Particularly, these were like signs of like some major sales that happened or something. Also, if they were repeating all the time, like, so we would want to like drill down into that to see if there's something that could be causing some of these dips and troughs that we're interested in explaining and figuring out why they're occurring. To the table on the right here kind of displays those transactions that are repeating and their numbers. If it's displayed with other, then it never repeated more than once. But they're all the large transactions that were defined as larger than $50,000. The biggest large repeating transaction being $83,360, which occurred almost 14 times a year across 4 years, which is pretty large. Further with the analysis of large transactions, but we looked at the frequency and mapped it out relative to the total transaction amount for two different periods that are really of note, kind of right next to each other. Every time that there's a trough in the overall transaction amount, there's a lack of large repeating transactions, as you can see from period fiscal year 22 and period 11 fiscal year 21. So those were really like glaring things that are missing from the troughs in the sales revenue. And then there's also just a really large uptick in large repeating transactions post-pandemic era, starting with fiscal year 2022, period 6. So from those large transactions, seeing that fiscal year period 6, fiscal year 2022 is generally when I would say the pandemic kind of came to not a close, but tapered off a little bit, the effects on business and everything. So we thought that maybe you should look into some COVID effects and get an idea of what's going on there, and charted out two graphs of the transaction count and transaction sum for those periods. Grouped these by 2 fiscal years back to back to get an idea of their, for pre-pandemic and post-pandemic, basically. The maximum and minimum occurred in fiscal year 2020 for both, which is really interesting. So pre-pandemic right here, fiscal year 2020 period 2 would be like November. So that's right before the pandemic hit, like, 5 months later. And then right after the pandemic hits, it experiences a minimum count in the amount of transactions going on. So definitely some significant amount of pandemic influences in this data set. And this company's like just general revenue stream. They were hit pretty hard. Being a manufacturing company kind of makes sense. Not a lot of workers are able to meet into large factories that are able to manufacture plastics. So for transaction sum as well, we saw that there was also a huge dip and a very significant difference in the yearly sum for fiscal year 2020 compared to any other fiscal year, 2021 even. But very interestingly, once 2022 hit, it had a very large, even though the count of transactions for 2020 was higher pre-pandemic. Post-pandemic in 2022, there was a larger revenue stream. So getting into the methods that we were used in this analysis, we have some testing, clustering, and then decomposition and modeling. So it started with Granger causality testing that was going to be there to determine some significant relationships between the total transaction amount and past transactions, like for isolating specific descriptions, like looking at CB, for example, whether or not lagging its description 1 transaction amount by a certain period could explain a trough that comes up. So like February 2023, like could we see if there's an uptick in the amount of transactions that happened for CB and description in fiscal year in November of fiscal year 2023, was there a lack of transactions then in February of 2023, simply because I was trying to analyze whether or not accounting practices, they were accounting for things in the wrong period, basically. That was a main focus of Joe's in this data set, and just trying to figure out if the accounting firm was just the accounting practices of the internal accounting department were just not correctly allotting for things in the accounts receivable. Also, then we got into clustering for PCA. We ran PCA for similar variance and k-means for similar data. For this data set, since it's extremely sparse, like I was mentioning, clustering worked a lot better than imputation. We got a lot more insights. Imputation was a mess. So we went from there. We used we then went into some seasonal decomposition to get the time series data plots into 3 different decompositions: trend, seasonality, and residual, to get some idea of like, is this explained by seasonality or is it randomness? Again, is this inaccurate accounting? Are we seeing some unexplained variation, or is there just like no seasonality, or is it everything explained by seasonality? And we use the seasonal decomposition to drive our modeling and our feature selection and prioritization. So for modeling, we considered 4 different models, or really 3: ARIMA and seasonal ARIMA, and then 2 ensemble models, random forest and gradient boosting. First performed feature selection on this, and then prioritizing which features using clustering. And then we had some variance prediction, and we optimized using grid search CV. For methods, we have PCA that was analyzed on description 1. Very immediately popped out for PCA. We've got the principal component, primary source of variability on the x-axis. CB, again, the description 1 that we saw earlier that popped out in the EDA, was really significantly different, showed a greatest variation by a factor of 6 compared to all other description 1s. EM and BK also were of note, like we saw earlier, not nearly as much as CB. To further confirm this, we conducted some t-testing on these 3 description 1s. So the table on the right shows the results of the transaction amount versus transaction amount with those description 1s transactions removed. So is there any significance in the difference in the data, in the variation of the data set, if those description 1s transaction amounts were removed? The only one that had a significant p-value for this was CB. So its removal from the data set just dramatically changed the rest of the data and its variance. So CB is, again, extremely significant. Similarly here to, as we saw with these, I listed all the constituent accounts for these 3 description ones, the main accounts that comprise their transactions. Account 5, 2, and 4 popped up. So I ran a PCA as well, just to get another idea of what accounts are coming up as well. And the same 3 accounts exhibited the primary sources of variation, particularly account 4. And similarly to description 1, we performed some account t-testing here to see what would be the difference if we removed these transaction amounts for these accounts from the data set and the variation. All 3 of them were significant, so there's no difference, but they were significantly different from removing any of the clustered rest of the descriptions at 352 descriptions. So there's definitely something going on in these 3 accounts and those 3 descriptions that I was mentioning. I then constructed a k-mean. I ran a k-means that kind of to reconfirm some of the PCA, just to get an idea of what's going on, as I mentioned in methods. K-means came up with very similar results. 3 distinct clusters came out, 4 distinct clusters, I should say, came out. 3 of them consisted of the same 3 description ones that we've been seeing from the very beginning: EM, BK, and CB. The other 352 clusters were 352 description ones were contained within 1 cluster. CB, I constructed this tree map just to get an idea of how much of the total transaction amount these 3 description ones are taking up versus the others. CB being taking up 46% of the transaction amount. So, even the other 352 only took up 32%. So there's definitely something going on there, that there's just like a very large account or a certain type of transaction. I don't have entire visibility into it. That's part of the issue with the data set, but just from a high level perspective, we can see that CB's got a lot of activity, and the accounts that are considered, that it is comprised of, being account 5, is really significant for the other 2. So we took the 3 description ones and clustered and grouped them together, which account for over 2/3 of the data set, 68% of the total transactions, compared to the other 352, which is only 32%. So moving on to seasonal decomposition, I conducted it both on the entire 4 years of the data set. And then due to the pandemic, COVID effects that we saw earlier that we're messing with, there's a very significant difference between the data and that's happened for the fiscal year 2020 and the rest of the years. So I decided to do a seasonal decomposition for 4 years, the past 4 years, and for the past 3 years. So this is past 4 years. The total here is the total transaction amount in thousands, and then by percentage, as we saw before. Those were broken down into trend plots, seasonal plots, and residual plots. The trend plot is similar across both. There's an upward progression. So you can see that this company might be experiencing some reliable growth, but we need to confirm that a little bit later. The seasonal plots are pretty interesting. If the seasonal was of the same scale or higher, the range of the seasonal was a bit of the same scale or higher than the residual plot, then there's definitely some significant seasonality to be looked at, investigated. Here for the transaction total amount, the seasonal plot was definitely around the same scale of the residual. So there's something interesting there, but not entirely like significant. Whereas for the residual plot, for the seasonal plot for percentage, it's of a pretty much lower scale, 30% range versus 40% range. So that not as much significance there. Transaction seasonality is slightly more significant than percentage seasonality for the past 4 years. But when we investigate the past 3 years and get rid of fiscal year 2020, we can really see that while the transaction plot's the same situation, with seasonal being of the same scale of residual, so significant but not, standard, like glaring smoking gun. Percentage plot was definitely a smoking gun with 40% range of the seasonal plot being 40% range versus only 10% for the residuals. So there's definitely a seasonal component here by percentage when passing the data set by percentage. So something to be considered here to see if we can explain these troughs, particularly fiscal year 2023, February fiscal year 2023, which was the main trough of note that we were investigating, and seeing if there is some seasonal explanation for this, which there seems to be. So we use the seasonal decomposition to drive our modeling. The transaction and percent revenue by period was used for all models. So I used both to just get an idea of what those would look like. The scoring metric that I decided to use was mean absolute percentage error. It's a relative measure of error. It required no past knowledge of transaction values to get a good threshold for like good performance versus bad. R-square just didn't give me as much insight. ARIMA models used the we used for the ARIMA models, my apologies. We used the auto-ARIMA function to optimize it. And we, as the seasonal decomposition suggested, we dropped fiscal year 2020. For the ensemble models, a 12-month feature window was created for every window, and that was to be able to have seasonality considerations similar to the ARIMA models. The first period started in fiscal year 2021, and we optimized with grid search CV, as I was mentioning. For ARIMA modeling, these were some of the results of all the models that we ran and their mean absolute percentage errors. The best one being a purely seasonal, but data set being past 3 years by percentage, with an MAP of 18%. So definitely, as we confirmed, as we had an inkling from the seasonal decomposition and seeing some seasonality there by percentage for the past 3 years, the best model that came out for the ARIMA was a purely seasonal plot. So definitely some seasonality to be explained. And just for good, good measure and for reference, I also created the other just 352 description ones and by the same methodology applied models to them to see what the best models would be. And they don't seem to have as much of a seasonal component at all. They don't have any seasonality in the best model that came up, and it was by transaction total as well. So with the MAP being a decent amount worse, 26% versus 18%. So these top 3 description ones by percentage for the past 3 years with a purely seasonal model was the absolute best model, ARIMA model that we could come up with here. Similar to the ARIMA model, we had an ensemble modeling that came up with, that we ran the 2 different types of models on percentage and transaction total. Mean gradient boosting regressor and random forest regressor. Not a significant difference between the types of models in terms of the mean absolute percentage error, but definitely a significant difference in terms of percentage versus transaction total, so the data type. So percentage just came up with a much better data, much better predictive model. The main difference here between the top 3 description ones and the other description ones modeling was that the other description ones were very, like all of the different types of models and data types that we passed that were very similar in mean absolute percentage error, but very different for the top 3 description ones in terms of transaction total and percentage. And yeah, as I was mentioning, the data structure here is that we use a window of the last 12 periods to determine seasonality and to determine the target feature of the current period. So also drilling back into some of the large transactions and some stationarity testing results that was necessary because Granger causality testing requires the time series to be stationary. Large transaction regression results came up with really no significant association with total transaction amount. It was a good thing for exploratory data analysis to like get an idea of where to look and what to do. But in terms of like using it for specific large transactions to predict some of these troughs, there was nothing significant that came out. For stationarity, there was something really interesting that came out with the trend plot that we saw with the seasonal decomposition that showed an upward trend. So confirming some of that growth that the private equity firm would look for in an acquisition target. The period scale of this time series for these transaction amounts was definitely not stationary. So there's something that could confirm that they're experiencing some sort of reliable growth, even though we saw in their original transaction plot and their revenue stream that it might visually not be trending upwards. It definitely is. For Granger causality, just a small note, we ran some of those lag OLS Granger causality models to see if some of the lag description ones would influence some of the troughs that we could see, or we could predict those troughs based on those lag transaction amounts. And only about 19.1% of the variation was explained. So I moved this to Appendix C. You can kind of take a look there if you'd like to. There's a large, robust analysis on this, but it ended up being inconclusive. So getting into some of the results, the ARIMA model results, as I was mentioning, is a completely seasonal model. So it requires a 12 period window to get to start making predictions. So you'll see a stagnant period in the predictions in orange here in the beginning. And then it starts to make decent predictions, especially when it comes to troughs, to get an idea of when those troughs occur. Particularly this trough is one that we've been investigating from the beginning, asked to investigate as well. You can see that these are just like, it's complete, everything here is completely seasonal. So it's confirming some of the idea that we are able to predict some of these troughs with a seasonal model. For Ensemble, we saw also a decent model that we could make. It used only a few months of forecast could be made from this, so it's not a large like 12 period window that like the ARIMA models, but we could make a decent prediction of each of the troughs using this with an MAP of 19.1% using the gradient boosting model. So in summary, for the results, the best predictors that we saw from testing were description ones by far. It was also validated by the count analysis just to get an idea. For clustering, the top 3 description ones that popped out were CB, BK, and EM, CB being the absolute most important. From seasonal decomposition, there was definitely an upward trend that was confirmed by Fuller testing. The time series of revenue for this company's general ledger transactions was not stationary, so it definitely had a trend line in some direction. Seasonal decomposition confirming that it's upward. And then there was some significant seasonality that came out of the seasonal decomposition as well. So we could confirm that there's seasonality. And then for modeling, the best model was post-pandemic, so the past 3 years by percentage using ARIMA. To conclude here, to answer the main concern of this project is the variability in the data set explained by seasonality or randomness? And we can say conclusively, well, first, sorry, I should say that we had to make some assumptions in answering that question. The pandemic, had a significant impact on business, so we had to make an assumption there. So by cutting out that first fiscal year 2020, then also we made an assumption that the 3 top transaction categories, CB, BK, and EM, drove the main variability in the revenue stream. Using these assumptions, we came up with the answer that absolutely based on the best model, seasonality was found to be the prominent component of the prediction. So you could confidently identify troughs using seasonality, a seasonal model. So this company is definitely experiencing some reliable revenue. To answer some of the private equity companies' concerns that we mentioned in the beginning, is the revenue stream volatile, as I'm saying? Yes, definitely. 66% of the revenue comes from top 3 description 1 transactions that were 41 times the average standard deviation, so pretty significant there. Is any of the component of this revenue stream inconsistent or sporadic? I would say no. We were able to consistently prove that it was heavily dependent on seasonality. And then finally, they want to know, is it have reliable growth? And yes, absolutely. Grouped by period, it's definitely not stationary, and from seasonal decomposition, we saw a positive trend plot. Though you never know, this could be post-pandemic trends. Like, we had to isolate and make an assumption that this is all post-pandemic. For some future application of this project and the analysis done here on other companies, which would be the entire point of automating this and being able to present this to private equity firms as like a decent solution, is that there's an applicable methodology that could be done for smaller mid-sized companies using the following steps, starting with feature engineering, transforming any transaction IDs that persist across multiple periods. You could perform some grouping and clustering things with predictors with the highest variation, and then decomposing everything using seasonal decomposition to get some idea from trends and seasonality, then conducting modeling on either ARIMA or Ensemble, ARIMA being the best to predict some seasonality, and Ensemble to get a good idea about trends. And this would expedite, it's a good blueprint for expediting the acquisition process, for the due diligence analysis acquisition process, I should say. Just to wrap up, some limitations in future work that were experienced here. Some limitations are, since I did not sign an NDA, I had some limited access to protocols and procedures, or I should say I was not offered an NDA to sign. Assumptions made about meaning had to be made about the meaning of all the features in here. So a lot of time was spent on exploratory data analysis just to get my head wrapped around what all these features meant, because it was just like a general ledger data full of things that I had never seen before, and just had to get an idea. And I had nobody to kind of explain exactly what everything was perfectly. You had to use general accounting principles as opposed to the specific accounting principles that might be used by this firm. Also, the data set size was really limiting. It's just 4 years worth of data. It would have been a lot better to be able to use a longer period of data, especially since most of it that we ended up finding to be useful was post-pandemic. That's also only 3 years, so it led to some limited insights. And then for future work here, I would say that I was asked to conduct some analysis on gross profit margin as opposed to total transaction amount as well, which you can see in Appendix B, the beginnings of that. When you convert things to gross profit margin over, the same troughs don't exist. February 2023 does not experience a trough in gross profit margin. It simply experiences a trough in total revenue. So that's something, you can't really make predictions on the task at hand using that. So there could be some further analysis done on that for sure to see if there's some way to use gross profit margin. Could focus on moving average to mitigate some of the sparsity of this data set. It was definitely a really, really sparse data set, which clustering helped with. CB itself could be investigated completely individually as opposed to grouping it with the other 2 description ones that were of note, EM and BK. Since it was so significant, 47% of the overall total transaction amount was comprised in CB by itself. It could be isolated. And then finally, you could also do some modeling for accounts, not just description ones. Here was mostly done through description ones models, split up, using the clustering methods that we saw, since those were more significant, but could definitely compare some models for accounts and description ones. And with that, I'll open up to Q&A. Thank you for listening.
Awesome job.
Thank you. Yeah, I appreciate it.
Questions from the floor?
Leland, congrats. Nice work. I was just curious what the timeline of this project was like for you, when it started,
Yeah.
and what were your and if you experienced, I mean, obviously you talked through a bunch of roadblocks and things like that.
Yeah.
But yeah, I'd be curious, like sort of how long it took from start to finish.
It took a long time. Yeah, this project, to give some background, I'm getting married in 2 weeks, and I was also doing some wedding prep and planning at the same time. But yeah, this project took, I would say, from start to finish, like about 6 months from getting the general ledger data. It was extremely complicated and robust. So I was commissioned. I think I was started it in October of last year. I was given the original automation of the visualizations to give. So I got a due diligence workbook from Joe. I finished that in about a week, and then I was kind of sitting on my hands for a couple of months there, just waiting for the general ledger data because there was some delay in the acquisition firm providing the general ledger data. I think they were cleaning things up and trying to get it over. It was a total mess for him. So he finally got that over to me in somewhere in, I think, January. So since January to today, that's where I've been hammering this out and trying to get a pretty robust idea of it. And yeah, it's been definitely really interesting. I've had a few meetings with him about it. And there's definitely something funky about it, but yeah, it's a long timeline. A lot of the exploratory data analysis was in the first couple of months, and then getting some idea of where to go from there was yeah, definitely around March was a good breakthrough. And yeah, definitely a long timeline.
Very cool. Nice work.
Yeah, thank you very much. For any other questions, yeah, please let me know.
Yeah, I have one. So, how much of, especially like on the modeling side, how much of this was stuff that you were already familiar with versus you had to just get up to speed with it for this particular project?
Yeah, so for the modeling side, I would say that I was very familiar with ensemble modeling. I already did a project on ensemble modeling, so that was pretty familiar. For the time series, I was already familiar with it from some of the modules that I was doing before getting this project. So, but in terms of actually applying it to a project, I hadn't had any experience with time series. So that was something that I had in Arima, was definitely something that was really new, novel to me in terms of real world application. So yeah, that I would say maybe 40% or about was probably new to me on this project. Yes.
Yeah, awesome. I know I've seen a few projects over the past year or so where people have thrown Arima at it because it was time series.
Yeah.
general impressions of the model?
Yeah, general impression of how Arima works on this. Yeah, it's definitely it was like a kind of a mess to figure out how to get some seasonal like trends to pop out from it. So as seasonal decomposition kind of came to me a little bit later. That was something I wasn't super familiar with in the beginning of starting this project. And I was really asked to just predict the seasonality in this data set. So it kind of drove me in that direction. But it was definitely, it was being fickle at first just to figure out how to understand if I could get a seasonal model at all. So like I had to like do a lot of trimming down of the data, finding out where, that cutting out for fiscal year 2020, like, doing some exploratory data analysis to see like where the difference is. Like there was a very big difference in the data from 2020 to the rest of the years, which I guess I should have known from the very beginning, but it took me a bit to kind of think along those lines. So yeah, it was really interesting. I think, and getting a scoring metric that was different. Also, I started off using R squared. The scoring it with R squared, I did a lot of research on outside of this to figure out like why the R squareds were just getting so poor, and a lot of it's just it explains that had to do with it. You're not supposed to use an R squared scoring metric for ARIMA models. So MAP was something that was a big breakthrough. It was just figuring out kind of like how to think about the scoring and what's a good model versus a bad model.
Awesome. Well, it all shows. So congratulations.
Yeah, thank you very much. Really appreciate it. Yeah, it was a lot of fun to work on this project. So I did enjoy like, just having almost no visibility into the data was something new to me. So just like working with like just numbers and letters was definitely different. So anonymized data is like a whole different animal. And I just thought that was actually kind of an interesting experience because I think that a lot of people deal with that all the time. So it's a good thing to get an experience in.
Absolutely. All right. Any questions for anyone else? All right. Well, congratulations on a wonderful project and also on getting married soon.
Thank you. Really appreciate it. Yeah. All right. Have a good one. Yeah.
Awesome. Roger, are you here?
Yeah, I am right here.
All right, great. Feel free to let's see, take over screen sharing.
Yeah. Sorry, let me just for you. I'm sorry, can you give me like 30 seconds?
For sure. Absolutely.
I apologize for that.
No worries.
Can you guys see this?
Yes.
Okay. So hi, yeah, I'm Roger, and I decided to do my capstone on computer vision to analyze soccer videos. So just a quick little outline of this presentation. So first I'm going to go around the background of like the models, why specifically I chose like soccer and like the rationale behind this whole thing. Then I'm going to go over like the tools I use to help me build the model. 3, we're going to go over the data set. Next, we're going to go over the iterations of models that led me to my final version. And then 5, we can talk about the metrics added in between each of the models. And then we're going to go into further work. And if anyone has any questions, then at the end, hopefully we'll have enough time so I can answer. So a little bit of background on computer vision in sports is like, why would you want to use computer vision in sports? So analyzing sports footage with vision capabilities is really helpful because it offers many advantages. So this can include performance improvement. This is because they can provide detailed objective analysis of players' movements and tactics. Oftentimes when you're playing sports, you're clouded, like you're in the moment, so there's a lot going on and you might not catch everything. Tactical insights. So the computer might see patterns that you might not see as a coach on the field. Objective evaluation. That's important because oftentimes emotions and the history of a player's career influences whether or not they play and their tactics. For example, even like with the Euros, with Germany, they have a top goalkeeper for the past 15, 20 years, Manuel Neuer, but their second string is arguably playing better. And he's probably not going to get a minute of the 2024 Euros. But with computer vision, you might be able to say that the second string would be better. In other applications, not specifically this project, you can get real-time feedback, specifically with the model that I'm using. This is crucial because if input with like a live stream, you can get real-time feedback. And this leads into the last point with scouting and recruitment. So if you have objective ways to evaluate prospective players, it then makes the evaluation of the player more accurate, and it supplements traditional scouting methods with more data-driven insights. So why the pretty much the model I used was the YOLO model, and it's a little different than traditional computer vision models. So the history of computer vision goes back several decades, and it goes as early as the 2000s. It reemerged, and ImageNet came with a challenge in 2010, and then AlexNet in 2012. And these were deep neural networks and the introduction of CNNs, convolutional neural networks, and those became the foundation for all computer vision models. And these drastically improved the accuracy and efficiency of image classification, object detection, and image segmentation. And then you move forward a little bit from the 2010s to now. There are a lot more frameworks and architectures that have been developed. Methods such as sliding window object detection, RCNN, which is region-based CNN, convolutional neural networks. Funny enough, the next one is called fast RCNN, and the last one is called faster RCNN. And the one that really took the industry by storm in 2015 was the YOLO model. And this is because it allowed for the real-time processing of the inputs. So YOLO can be used in many things, such as sports, autonomous driving, surveillance, and medical imaging. So with YOLO, in this specific case, we're using it for player detection and tracking. This helps analyze player movements, formations, and interactions. It helps with ball tracking, for example, in other sports such as tennis, cricket, or basketball, baseball, or even football, where you're throwing the ball. It helps with event detection, so it can detect whether or not you're shooting a basketball, shooting a soccer ball, like in the action for a pass or something. Automated officiating systems, such as in tennis and VAR and soccer, and enhanced analytics and visualizations. So what really makes YOLO different is, so they have this structure pretty much where you only look once. That's what the acronym stands for, but it's different than traditional CNNs because those use layers upon layers to build different segmentations, I believe, and that builds into a final layer which tells you the classification. But this algorithm breaks the image down into 9 different grids, or 16 grids, 4x4, depending on the image size. Either way, it tells you, it finds bounding boxes, and from those bounding boxes, it gives you the confidence that the object within the bounding box, if it's centered, is either, for example, 1 could be a dog, 0 could be human. So the label for either of them could be like 1 or 0. Little history about YOLO. So first YOLO came out in 2015. It was developed by Joseph Redman and presented a unified architecture for object detection that significantly outperformed traditional methods in terms of speed. Then YOLO v2 was released. It was also known as YOLO 9000, I believe. It was released in 2016, and it improved the original model by incorporating batch normalization, anchor boxes, and dimension clusters. Then you had YOLO v3 launched in 2018, and it further enhanced the model's performance with a more efficient backbone network. It introduced the concept of feature pyramid networks for better detection at different scales and improved bounding box prediction. YOLO v4 was released in 2020, and it introduced mosaic data augmentation, a new anchor-free detection head, and a new loss function. This was led by Alex Botchevsky. I'm definitely pronouncing that wrong, but they incorporated advancements such as the CSP Darknet 53 backbone and other various techniques to improve accuracy. And the model that I chose for this specific project was YOLO v5, and this was the first model developed by Ultralytics. And they further improved the model's performance and added new features such as hyperparameter optimization, integrated experiment tracking, and automatic export to popular export formats. So in the end of the project, I exported all of my videos in MP4 format. It was really popular because it's known for its ease of use, its state-of-art performance, and practical considerations such as the size of the model, the deployment capabilities, and the ability to integrate into many frameworks. YOLO v6 was sourced in Meituan in 2022, and it's used in industry nowadays in the company's autonomous delivery robots. YOLO v7 is added in 22 of July, and it just improved. And YOLO v8 is the latest YOLO by Ultralytics. However, oftentimes it doesn't perform as well as YOLO v5, although I think it has more general like some skills it's better at. I heard it was better at dense smoke and recognizing certain things. And then YOLO v9 and 10, YOLO v9 just recently came out, so it's still technically in development if you're making updates and stuff like that. And YOLO v10 is still being researched to this day. So the libraries that I used to build the model, I used Ultralytics because of the ease of use, and then OpenCV. OpenCV is an open computer vision library that is available to everyone. NumPy and Pandas for data manipulation, and then Supervision to help me with the tracking between the frames. So here we can go over to a quick dashboard that I made. So if we go to this video right here, this is the raw video of what I used. So the data set is found on Kaggle. This was a Bundesliga data set, and I used one of the videos. So here is the original video that I would input into the. So you see here, the camera's moving with all these players. Yeah. And then we move over to the out of the box model, the base model. And this is YOLO doing pretty much the bare minimum it can. And we can see here that the problem is we have tracked people who are not in the game. And the ball here is not currently being tracked. And we want that. So what we ended up doing is we ended up training. When I ended up training is because I don't have a GPU, I had to go to Google Colab. And in Google Colab, I ended up buying one of their virtual GPUs and training the data set over there. And after the training, it and some label changing, or with the labels that were provided by RoboFlow. I got the training data from roboflow.com. On the cloud, I just downloaded it over. And then with the labels of the data and the training, it output this next video. So we see here that the ball is a little better tracked. Like it's just, there's no certain way to say that the ball is better tracked, but it seems that way. And these people on the sideline now are not being tracked, and as well as it distinguishes the difference between referee and the players. So the next thing I did is, because this thing, the formatting of the presentation here is a little bit difficult to read and difficult to interpret here, I ended up changing the icons like in FIFA, and I added the track ID to each of them on the bottom. And this also allowed me to start tracking objects through frames and moving, and allowing each player to have their own respective icon. And I also kept a track on the ball here. But as you can see here, the ball is still being lost when it is being passed sometimes, although it is better, I would say. Ball's being dragged. So the next thing I did is, because each of these guys now have a track ID, I can do the colors of each of the players here, and I can make the corresponding colors their icon color as well. So what I did for that is I took the bounding box of each of the tracks, and I took the top half, because the bounding box has the entire player in it. So if I figured that if I took the top half of the player, it would have only the kit. And what I did there is, in the four corners, 1, 2, 3, 4, I took the pixels, took the average RGB value there. And then because of the way the bounding boxes work, all of them turned out in the way that the corners of the bounding box are going to be the background, and that's one color. And then I ended up setting up a k-means clustering, and there were two clusters, one being the background and one being the player. And what I did is I just took the average color of each of those two clusters. And so for each of the two players, there's the two teams, there's the corresponding color, and that's seen here. But the ball is still kind of going off. So what I tried to do next is to solve the issue with the ball not being tracked all the way. So what I did here is I tried to interpolate where the ball would be. So for example, for 9 to 13, it's going from 9 to 13. And even if it does skip a few frames, if the frame before and the frame after tracks the ball, then we could logically assume that the frames in between are also where the ball is supposed to go, because many of these passes are on a straight line. So we can just, as long as the gap isn't too big, we can interpolate where the ball should be. So we can just kind of estimate where the icon should be at the period in time. And it is a lot better. So like here, the ball isn't being lost anymore. But there are some points where it gets a little jumpy here. And that's through the method that I interpolated the ball. But it's a lot better than what it was before. Yeah, right there, it was a big jump. So next thing I did is I added a possession icon. So now whoever's holding the ball can actually be seen here. And that allows for a lot of things, because it points out who has the ball, which team has the ball, and the amount of time based on like the duration of the video and how often I set the frequency, or like the frequency. And here you see the ball is here, and then here, and here. And because we have now whoever possesses the ball as well as the teams and where the ball is, we can determine the possession. So here we see that only the white team has touched the ball, so it's at 100%. And there's a little bit of jitter here, and that's because of the model trying to recognize, like reclassifying this guy over and over again for some reason. But that's just due to error in the model, I guess, and that can be further improved upon. But yeah, according to this, approximately 2/3 of the time, or 3/5 of the time, the ball was in team 2, or the beginning guy. And then the next statistic I wanted to add was actually the distance moved, as well as the relative, like the estimated speed that each of these guys are running at. But to do that, it becomes very, very difficult because the way the camera is angled, we can see through, I did a little bit of analysis here. So this is the midpoint right here of the soccer ball, or the soccer pitch. And the number of pixels from this midpoint to the top and the number of pixels from this midpoint to the bottom aren't equal. So I ran a little bit of a where we calculate for the camera shift here. So like based on how the camera shifts, the positions move to counteract that. And there, theoretically, we should be able to estimate the total distance moved, as well as the total distance moved, as well as the speed at which the players are moving. Visually here, it looks no different. It's just all calculations done behind the scenes. Go here. And then the last model I added is I added the panel here. I'm sorry. And then this is with the position adjusted shift. So this is with the adjusted position here. And because we have the adjusted position scaled in the right way, we can go here and do the relative speeds of all of the players. I only did this region here because of this is where a majority of the players were, and only really where we had the scale here. These would scale out in a different way. But it leads to this right here. So it keeps track of speeds, distances, icon, referees, possession, and whatnot. So pretty much to recap, we started out with the raw video, then we moved to the base out of the box model here, trained it, made it a little more appealing to the eye, made it more easy to read, added the team colors so it looks also a little bit nicer, interpolated the ball so the frames that were the ball were lost were able to be estimated at least. Added the possession icon right here, that little red guy on top of 13. Because of both of those, we were able to track the possession. And then because we wanted to calculate the speed, we had to calculate for the camera shift. And this is with the calculations done and with the estimated speeds and the distance moved. So further work on this project can be a better way to estimate the camera angle and the shift. The way I did it, I feel like was very crude. And same with the ball interpolation. As you can see in the videos there, sometimes the ball jumps a little bit forward. That's because I think the way I implemented it is, if it's the first one, then you just take the ones on the outsides and just interpolate in. So it's like that. But that can definitely be improved upon. And the speed calculations and the distance calculations moved can definitely be improved because the camera angle estimations can be improved. We can also further expand upon this is can formulate an algorithm which can expand into real-time player evaluation. That could be a thing. I think I would need to restructure this a lot. It could also be formulate an algorithm to predict what is going to happen next, so like patterns and stuff. And yeah, so if given live data, can make predictions for final score, winner of the game, and predictions for player stats. And yeah, that pretty much concludes it. Does anyone have any questions?
Awesome job. So, I have a few thoughts, and then maybe I'll get to a question too. Like one thing, and I don't know if this will work for your use case, but one of the things for dealing with like camera position and other things, have you heard of the algorithm called SLAM?
I have not, no.
So it's like semantic location, something, something, something. But basically, it's used often for if you have, say, a dash cam for a car and you're driving forward, it can actually create like a 3D map of everything based just on subsequent video frames. I don't know how well it works for like horizontally panning versus like translating, but it might help you. I'm not sure.
Yeah, I'll definitely look into that. Thank you.
Yeah. Second, so for the you added the IDs of the players that you're tracking. Now, the where did the numbers actually come from? Was it based on like associated actually with the player, or just like the location array?
Right. Yeah.
Yeah.
That is.
So there's something that might help with this. I don't know, especially like these videos are so zoomed out, so maybe it won't. But there's a an entirely different project there. It's on GitHub. You can look for it. It's called Crop Clip. And just as an inspiration for this, what it does is it pairs YOLO with the OpenAI clip model, where you can basically use the bounding box to get out an image, embed that image, and then search for other things. So if you were able to take like the image of the player within the bounding box and then compare it to, I don't know, like look for their jersey number or something like that. Again, the video resolution might be too low for that, but that might allow you to say it's like, you know, who is who. Like you have the IDs here, but actually pairing it universally to someone. If you had a database of like all footage of all the people cropped to the bounding box, that might work.
That, yeah, no, that's really cool. I've never heard of that.
Yeah,
that's
I've dealt with this stuff for a while. But yeah, other questions? Well, yeah, I mean, I think this definitely could be useful for a number of, I mean, all the things that you talked about. And like, if it is possible to extend it to like knowing actually what player is where, then you can do things like incorporate separate, like the stats of that player. Like, you know what team it is, so we know what number, you can look up other things. You can track their stats in real time if you really wanted to. I don't know. Uh, yeah, I mean, and I feel like this is fairly easy to extend to other sports as well.
Yeah, I was gonna comment that too. I know it can be used in at least tennis.
Yeah.
And I can't imagine why it wouldn't be able to be used in basketball and other. Football might be a little crowded after like a tackle in the middle, but yeah.
I think it would also depend on what video feed you have. If you're doing like broadcast, they're gonna cut it out a lot. Soccer is pretty static with all of these. If you actually had a fixed camera, or not necessarily fixed, but like, you know, the wide angle that's just tracking things like that, for pretty much any sport, you might be able to do it. Which basketball definitely, like you said, is a lot of that. Football tends to not be. Tennis, yeah. But yeah, definitely. I guess a sport that would not, no, it's not a team sport either, but like golf would be hard.
Yeah.
Yeah. Well, wonderful. Congratulations.
Thank you.
If there's nothing else, I guess that does it for today's presentations. We had a lot and it was all awesome. So thank everyone for coming. Congratulations to everyone who this is their capstone, you included. It's a long journey, but you've made it.
Thank you, Cole.
All right.